Welcome, curious minds and sleepy thinkers. You found a soft place to land where the questions are big and the pace is slow enough not to jolt you out of your pillow cocoon. Tonight, we're going to tiptoe into one of the most mysterious questions ever asked. What lies beyond the edge of the universe we can see, but don't worry, we'll take it slow. This isn't a race through equations. It's more like floating through a galaxy of ideas with a cup of chamomile tea. The concept of the observable universe is our gentle starting point, a vast familiar home we've come to know, yet one that stretches further than our imaginations can truly grasp. It isn't the entirety of existence, but simply the portion from which light has had sufficient time to reach our watchful eyes and sensitive instruments. Imagine, if you will, the universe beginning with a single soft whisper, a primal sound of light emanating from a singular point. This whisper, this first gleam, has been steadily traveling outwards, expanding its reach across the cosmos ever since that initial moment. Our observable universe, then, is precisely the bubble of space that this ancient whisper of light has managed to fill. Every star, every galaxy, every wisp of cosmic dust within this shimmering bubble has sent its own unique message of light on an incredibly long journey. A journey that has at last culminated at our cosmic doorstep. This notion of a cosmic doorstep can at first feel a little disquieting, suggesting a definitive boundary, an invisible wall that prevents us from seeing further. However, it is crucial to understand that this is not a solid physical barrier in the fabric of space itself. Instead, it is a fascinating and beautiful limitation woven from the very essence of time and light. Picture yourself residing within a venerable old house, perhaps a century old, and you desire to know what transpires beyond its walls. You are constrained to perceive only as far as the sunlight originating from your location can travel and return to you. You could never truly grasp the events unfolding on the opposite side of the planet, for the light from those distant places would simply take too long to complete its arduous journey back to your vantage point. Our universe, in its own grand cosmic timeline, is approximately 13.8 billion years old, and light, as we know, travels at a finite, unyielding speed. Therefore, there exists an intrinsic cosmic horizon, an inherent limit to the farthest reaches we can ever hope to observe and comprehend. This magnificent boundary meticulously defines our cosmic dwelling, our precious bubble of perception. But it emphatically does not signify an end to the universe itself. It merely implies that there are vast uncharted territories of the universe from which we have yet to receive even the briefest of postcards. This bubble of our observable universe, though a seemingly snug haven for our contemplative minds, is by no means a diminutive space. You might quite logically assume that since the universe is 13.8 billion years old and light has been traveling for all that time, our cosmic home would simply be a neat sphere of 13.8 billion light years in diameter. Yet this is precisely where the narrative becomes even more captivating, imbued with a dreamlike quality that stretches the very limits of our intuitive understanding. While that ancient light has indeed been journeying for eons, the universe itself has been in a constant, relentless state of expansion, stretching outward like a colossal rubber sheet, pulled taut by an invisible hand. The very galaxy that first emitted a slender beam of light, 13.8 billion years ago, has, in the intervening epochs, migrated significantly farther away from us due to this ceaseless cosmic stretching. Consequently, the observable universe we perceive today is not a quaint, precisely defined, a 13.8 billion light-year sphere. Instead, it is an expansive, almost inconceivably vast expanse, estimated to span an astonishing 93 billion light-years across. It represents a distance so unfathomable a journey, so protracted, that our human minds must ultimately release their grip on mere numbers, and instead surrender to the sheer breathtaking wonder of its colossal scale. Within this magnificent, ever-stretching cosmos, there resonates a constant, almost hypnotic hum, an ancient melody that we can still faintly perceive. It is a profound relic of the universe's earliest, most primordial moments, the very first light that our telescopes have ever managed to coax from the depths of time. This ethereal glow is known as the cosmic microwave background (CMB) radiation. To truly grasp its significance, imagine the universe in its infancy, a minuscule, incredibly dense, and unimaginably hot entity, a blindingly brilliant ball of pure plasma. For approximately 380,000 years following its genesis, the universe remained so incredibly hot and densely packed that the nascent light particles found themselves utterly unable to move with any semblance of freedom. They were in a perpetual state of collision and constantly bumping and rebounding off other particles, much like being hopelessly lost within the impenetrable depths of a thick swirling fog. Yet, as the nascent universe continued its inexorable expansion, it gradually began to cool. With this gentle cooling, the cosmic fog slowly but surely began to dissipate and clear. And at that precise momentous juncture in cosmic history, the very first photons of light were finally set free. This liberated light has been journeying across the cosmos ever since, gradually stretching its wavelength and gracefully fading in intensity over the intervening billions of years. Today, when we observe this ancient light, we no longer perceive it as the blinding brilliance of its birth. Instead, it manifests as a faint, uniform glow of microwaves permeating the entire sky, an omnipresent echo of the universe's very first breath. It is a silent testament to a time when the universe was barely a toddler, offering us an invaluable direct glimpse into its earliest, most formative moments. The CMB isn't just an ancient echo. It's a profound map, a cosmic canvas painted with the subtle nuances of the universe's infancy. While it appears remarkably uniform to the naked eye of our instruments upon closer inspection, it reveals tiny, almost imperceptible fluctuations in temperature. These minute variations, like the gentle ripples on a perfectly still pond, are of monumental importance. They are, in essence, the earliest seeds from which all the grand structures of our universe eventually grew. Imagine a vast, perfectly smooth, cosmic pudding. If there were no tiny lumps or imperfections in that pudding, it would simply remain a uniform, featureless expanse. But the CMB shows us that there were indeed these minuscule lumps regions that were ever so slightly denser or cooler than their surroundings. Over billions of years, gravity, that relentless sculptor of the cosmos, worked tirelessly on these tiny initial differences. The slightly denser regions began to attract more matter, slowly drawing it in, growing larger and larger. These humble beginnings eventually blossomed into the magnificent galaxies, the colossal galaxy clusters, and the vast, intricate cosmic web that interweaves the universe as we know it today. The CMB, therefore, is not merely an ancient whisper. It is the fundamental blueprint, the primordial genetic code from which the entire cosmic tapestry was meticulously woven. It tells us about the very first moments, about the conditions that prevailed when the universe was just a baby, offering us an almost direct connection to its earliest, most profound secrets, and what drives this incredible, relentless journey of expansion. What keeps the cosmic balloon inflating, pushing the galaxies ever further apart? This brings us to one of the deepest, most enigmatic mysteries of our time: dark energy. For centuries, we believed that gravity, the universe's great attractive force, would eventually slow down the expansion, perhaps even pull everything back together in a cosmic big crunch. But then, about 2 decades ago, our observations delivered a startling, almost unbelievable revelation. The universe wasn't just expanding, it was accelerating its expansion. It was speeding up as if some invisible pervasive force was pushing everything apart with ever-increasing vigor. This mysterious repulsive force, this unseen hand on the cosmic throttle, is what we call dark energy. Imagine trying to understand a complex machine when 2/3 of its parts are completely invisible to you. That's our situation with dark energy. It makes up an astonishing 68% of the universe's total energy and matter content. Yet we have no direct way of observing it, no simple instrument that can pick up its signal. We only infer its existence and its immense power from its gravitational effects, from the way it relentlessly stretches the very fabric of space, pushing galaxies away from each other at an ever-increasing rate. It's like feeling a strong wind, but never seeing the air itself. Dark energy acts as a counter-gravitational force, defying the natural tendency of matter to clump together. Without it, the universe would have likely collapsed back on itself long ago, or at least its expansion would have slowed to a crawl. Instead, it is the dominant force in our cosmos guiding its ultimate destiny, an unseen maestro conducting a symphony of separation. This incredible pervasive force is not only shaping the universe we observe, but its relentless push is also directly influencing the boundaries of our observable universe, constantly expanding the horizon of what light can reach us from. As space stretches, light has a longer and longer journey, and the more rapidly space stretches, the harder it is for light from the very edge to ever make it to our cosmic shore. The very foundation of our understanding of these incredible cosmic distances rests upon a bedrock of human ingenuity and relentless observation. When we speak of a light year, we are not merely talking about a unit of distance. We are invoking a concept of time woven into the fabric of space itself. A light year is the vast, almost unimaginable distance that a single ray of light, traveling at its immutable cosmic speed of approximately 299,792,458 meters per second in a vacuum, covers in the span of one Earth year. To put that into a more grounded perspective, it's roughly 9.46 trillion kilometers, a number so colossal that it quickly loses all meaning for our terrestrial minds. This measurement serves as our fundamental cosmic yardstick, the indispensable tool that empowers astronomers to navigate the seemingly boundless reaches of space, mapping out the distribution of galaxies and charting the course of cosmic evolution. Without this precise understanding of how light behaves over vast distances, our attempts to comprehend the scale of the universe would be akin to trying to measure an ocean with a thimble. One of the most powerful and elegant tools in the astronomer's formidable arsenal for gauging these immense distances is the observation of type Ia supernovae. Imagine these celestial explosions as cosmic lighthouses, each one possessing a remarkably consistent, almost identical intrinsic brightness. These stellar explosions are not just random bursts of light. They are the spectacular death throes of certain types of white dwarf stars that have accumulated matter from a companion star until they reach a critical mass, triggering a runaway thermonuclear reaction. Because the physics governing these specific explosions is so well understood, every type Ia supernova releases a predictable, standardized amount of light. This makes them invaluable as standard candles across the cosmos. By meticulously measuring how bright one of these supernovae appears from Earth, astronomers can, with remarkable precision, calculate its exact distance from us. If a supernova appears dimmer, we know it's farther away. If it appears brighter, it's closer. It's a cosmic trick of perspective, but one that allows us to pierce through the veil of astronomical distances and place these brilliant markers firmly on our cosmic map. But the story of distance measurement doesn't end with brightness alone. There's another equally crucial piece of the puzzle, a subtle shift in the very light itself that whispers secrets about the universe's relentless expansion, the phenomenon of redshift. Imagine the sound of an ambulance siren as it approaches you, its pitch high and piercing. As it passes and recedes into the distance, the pitch drops, becoming lower and deeper. This is the Doppler effect. Light, too, experiences a similar effect. As a source of light, like a distant galaxy, moves away from us, the light waves it emits are stretched out much like a rubber band being pulled. When light waves stretch, their wavelength increases, shifting towards the red end of the electromagnetic spectrum. This is what we call cosmological redshift. It's not just the galaxy itself moving through space. It's the very fabric of space between us and the galaxy that is stretching, carrying the light wave along with it. By meticulously measuring the redshift of light from distant galaxies, astronomers can deduce the rate at which the universe is expanding at that particular point in space and time. A greater redshift indicates a faster rate of recession and thus a greater distance. This ingenious method provides a direct measurement of the universe's expansion rate and consequently allows us to estimate its overall size and how far its ancient light has traveled. It's like having a stretching tape measure that tells us not only how long something is, but also how much the tape itself has expanded since we started measuring. This subtle shift in color, this cosmic sigh of expansion, is one of our most profound clues to understanding the dynamic, ever-changing nature of our universe and its immense proportions. The cosmic microwave background. CMB radiation, that faint ancient glow we spoke of earlier, serves as an even more fundamental cornerstone for measuring the observable universe. Imagine it as the universe's earliest selfie taken just 380,000 years after the Big Bang. This isn't just any old photograph. It's a snapshot of the cosmos when it was incredibly young, before any stars or galaxies had even begun to form. At this tender age, the universe was a relatively simple uniform soup of particles and light slowly cooling and expanding. The CMB reveals itself as an almost perfectly uniform warmth across the entire sky, a testament to the incredible smoothness and homogeneity of the early universe. Yet nestled within this uniformity are meant almost imperceptible fluctuations in temperature, tiny wrinkles on the otherwise smooth fabric of the primordial cosmos. These incredibly subtle fluctuations are absolutely crucial. They are not random noise. Rather, they are the direct imprints of the earliest quantum fluctuations magnified to cosmic scales during the period of cosmic inflation, a concept we'll gently explore later. By meticulously analyzing the pattern and magnitude of these minute variations in the CMB, scientists can infer the universe's overall geometry, whether it is flat-curved like a sphere or curved like a saddle, and its precise expansion rate. It's like being able to tell the shape and size of an entire ocean by carefully studying the patterns of its ripples on a single day. These observations, combined with our most sophisticated mathematical models of the universe's expansion, allow for remarkably precise calculations that estimate the observable universe's extent, giving us a grand sense of the cosmic bubble we inhabit. The CMB, therefore, is not just a glimpse into the past. It is a fundamental calibration tool, allowing us to triangulate our position within the vastness of space and time. The incredible precision and depth of our understanding of the observable universe are largely thanks to the breathtaking advancements in technology. Our ability to peer into the farthest reaches of space has been significantly bolstered by the development of extraordinary telescopes, both those firmly anchored to our planet's surface and those gracefully orbiting in the silent vacuum of space. These aren't just giant magnifying glasses. They are intricate, highly sensitive instruments equipped with advanced sensors and cameras, capable of capturing light across an astonishing array of wavelengths. Gone are the days when we relied solely on visible light, the narrow band of colors our human eyes can perceive. Today, our cosmic eyes can detect faint whispers from across the electromagnetic spectrum, ranging from the long, gentle undulations of radio waves through the warm embrace of infrared light, the vibrant energy of ultraviolet rays, all the way to the intense, piercing gaze of X-rays and gamma rays. This multispectral observation is akin to experiencing a symphony with a full orchestra, rather than just a single instrument. Each wavelength of light carries unique information revealing different aspects of the universe that would otherwise remain veiled. For instance, radio waves can penetrate the thickest dust clouds, unveiling regions of new star formation hidden from visible light. Infrared light allows us to see through the cosmic dust and gas, revealing the earliest, most distant galaxies whose light has been stretched by the universe's expansion into longer, redder wavelengths. X-rays and gamma rays allow us to probe the most energetic and violent phenomena in the cosmos, such as exploding stars, supermassive black holes devouring matter, and collisions of entire galaxy clusters. This comprehensive multi-wavelength approach provides us with a far more nuanced, incredibly rich understanding of cosmic distances and the nature of the objects that inhabit them. It allows us to uncover the universe's hidden facets, piecing together a more complete, vibrant tapestry of our cosmic home, revealing objects and phenomena that simply remain invisible in the traditional optical range. And as we delve deeper into the intricate dance of cosmic distances, we find ourselves inevitably guided by the profound wisdom of Albert Einstein's theories of relativity. These revolutionary theories, particularly his general theory of relativity, which elegantly describes the interplay between gravity, space, and time, offer a fundamental framework that allows scientists to continually refine their measurements of cosmic distances with astonishing accuracy. Einstein's insights are not mere abstract concepts. They provide concrete predictions about the universe's large-scale structure and its dynamic evolution, helping us understand how light travels through a universe that is both expanding and teeming with massive objects. One of the most captivating phenomena predicted by Einstein's theory, and now routinely observed by astronomers, is gravitational lensing. Imagine a massive galaxy cluster, an enormous collection of galaxies, bound together by their collective gravity, lying between us and an even more distant object, such as a very distant galaxy or a quasar. According to general relativity, this massive cluster acts like a cosmic magnifying glass. Its immense gravitational pull warps and bends the fabric of space-time around it, causing the light from the more distant object to bend and be focused much like light passing through an ordinary lens. This gravitational lensing effect is not just a beautiful cosmic optical illusion. It is an incredibly powerful tool for astronomers. By meticulously studying the way light is bent and distorted around these massive gravitational lenses, scientists can precisely measure the mass of the intervening galaxy clusters. And crucially, by understanding the mass and distribution of these cosmic lenses, astronomers can then infer the distances to both the lensing cluster and the lensed object, even if that lensed object is incredibly far away beyond what we might otherwise detect. It's like having a cosmic ruler that uses the very curvature of space-time to measure the vast stretches of the universe. Furthermore, these theories explain how gravity not only bends light, but also influences the very passage of time, an effect known as time dilation. While time dilation is more pronounced near extremely massive objects like black holes, the principles of relativity are essential for calibrating our observations over the vast gravity-infused expanses of intergalactic space. Thus, Einstein's profound insights provide the essential theoretical scaffolding upon which our entire understanding of cosmic distances is built, pushing the boundaries of what we can measure and comprehend in the universe. The observable universe, our known cosmic home, is a place of breathtaking wonder and unfathomable scale. It is mostly empty space, a vast, silent canvas upon which galaxies are scattered like luminous islands in an immense dark ocean. Our own galaxy, the Milky Way, is but one of billions each, a swirling maelstrom of stars, gas, and dust, bound together by gravity. These galaxies, in turn, host a countless myriad of stars each, a tiny burning furnace in the cosmic night. And around many of these stars, we are now discovering revolved planets, worlds of unimaginable variety, some barren and desolate others, potentially teeming with the very ingredients for life. The sheer number of stars within our observable universe is a concept so vast that it truly humbles the mind. Imagine trying to count every grain of sand on every beach across every continent on Earth. Now try to imagine that number being dwarfed many times over by the sheer multitude of stars in the observable universe alone. It's an astronomical comparison that speaks volumes about the universe's unimaginable scale and its profound, unending generosity in scattering these pinpricks of light across the vastness. Each star a potential sun, each planet a potential world. The composition of this observable universe, from the grand cosmic web down to the smallest hydrogen atom, is a testament to the intricate balance of forces and the endless possibilities that unfurl within this boundless cosmic expanse. Now let us gently drift beyond the edges of this familiar observable universe, venturing into realms where the light from its very beginnings has simply not yet had the time to reach us. Imagine standing on the shore of a vast, tranquil ocean, gazing out at the distant horizon. You can see the sunlight dancing on the waves for miles and miles, but you know deep in your heart that the ocean stretches infinitely further beyond what your eyes can perceive. These unseen waters, these regions unreachable by our current observational technologies, hold a tapestry of cosmic mysteries and theoretical wonders, an unexplored frontier brimming with the promise of unraveling the most fundamental questions about the universe's very nature and its ultimate, magnificent fate. It's a space where our direct view ends, but where the landscape of possibility truly begins to unfold. Just beyond the luminous reach of our most powerful telescopes, cosmologists allow their imaginations to take flight, gently speculating about the quiet existence of other galaxies, perhaps even other stars and planets waiting in the cosmic stillness. But the contemplation doesn't stop there. They whisper of something even more profound, the possibility that in these distant, unobserved territories, the very physical laws or constants that govern our corner of the cosmos might subtly or even dramatically differ. Imagine a universe where gravity is a touch stronger, pulling everything into tighter, denser formations, or where the speed of light is slightly faster, allowing information to travel with even greater alacrity. Such variations would fundamentally reshape the celestial ballet we observe, leading to cosmic landscapes that are both breathtakingly similar and yet profoundly alien. These hypothetical realms tease the very fabric of our understanding, inviting us to consider a cosmos far grander and more diverse than our current perceptions allow. And this gentle contemplation leads us quite naturally to one of the most enthralling concepts to ever emerge from the quiet corners of theoretical physics, the multiverse. It's not a single grand all-encompassing universe, but rather a collection, a boundless tapestry woven from perhaps multiple, perhaps even infinite universes, each with its own unique properties, its own distinct hum. Imagine our universe as a single dewdrop glistening on an infinite spiderweb. Each dewdrop is a universe, separate yet connected by the unseen threads of the greater multiverse. This theory, this cosmic whisper, delicately teases the imagination, suggesting that the very reality we inhabit is but one of countless possibilities. Each of these individual universes, these unique dewdrops, could harbor its own peculiar physics, its own distinct set of fundamental forces, its own strange and beautiful forms of matter. They could present alternative versions of reality where the rules of existence are subtly or even drastically different from our own. Perhaps some universes are silent, devoid of stars, while others blaze with an intensity beyond our wildest dreams. The multiverse concept isn't just a scientific idea. It's a philosophical canvas, challenging our most deeply held understandings of existence itself, inviting us to humbly acknowledge the vast, unimaginable diversity that might lie just beyond our perceptive grasp. As we peer into these unobservable regions, the quiet giants that continue to perplex scientists cast their long, enigmatic shadows, dark matter and dark energy. Within our observable bubble, we can infer their mighty presence not by seeing them directly, but by observing their profound gravitational effects on the visible matter around them. We see galaxies spinning faster than they should, held together by an unseen embrace. We witness the universe's expansion accelerating, driven by an invisible push. But their true nature, their intrinsic essence, remains meticulously hidden beyond our observable limits. Imagine trying to understand the inner workings of a grand clock by only observing its hands and the way they move. You know there's intricate machinery beneath the surface driving the motion, but you cannot see the gears, the springs, the delicate balances, these mysterious components. Dark matter acting as the universe's silent gravitational architect and dark energy as its accelerating engine could exhibit behaviors or properties in the unseen realms that are entirely new to us. Perhaps in those distant unobserved reaches, dark matter interacts with itself in ways we haven't yet conceived, forming strange ghostly structures. Or perhaps dark energy itself shifts and changes, manifesting with different intensities or even different fundamental properties, leading to wildly different cosmic outcomes. These unknown aspects could hold the crucial keys to unlocking their profound mysteries, potentially reshaping our entire understanding of the universe's fundamental structure and its dynamic evolution. It's a humbling thought that the majority of our universe is composed of elements about which we know so little, and that their true secrets might lie in realms we cannot yet touch with our telescopes. The silent, invisible dance of dark matter and dark energy beyond our view is a powerful reminder of how much remains to be discovered, a gentle invitation to embrace the unknown. Then the mind, free from the constraints of immediate observation, begins to gently ponder a truly tantalizing question: the very shape and ultimate extent of the universe. Is it truly infinite, stretching outwards forever, a boundless tapestry woven without end? Or does it perhaps gracefully loop back on itself in an unimaginably vast curvature like the surface of an enormous cosmic sphere, where a journey in one direction would eventually bring you back to your starting point, yet from a different angle? Or could it possess a defined boundary, a cosmic edge beyond which lies? What these questions are like trying to imagine a landscape from within a single tiny, perfectly formed dewdrop. We can perceive the beauty and complexity within our drop, but what does the rest of the vast unseen garden look like? The scientific theories abound, each a delicate thread woven into the fabric of our understanding. Some cosmological models suggest a flat, infinite universe stretching out forever like an endless calm sea. Others propose a positively curved closed universe, finite, but without boundary, like the surface of a giant balloon. Still others consider a negatively curved open universe extending infinitely, but shaped like a cosmic saddle. But without the ability to observe these regions directly, without the power to truly touch those distant shores, these profound questions remain wonderfully speculative. They exist as a boundless frontier of human curiosity and scientific inquiry, a vast open space for our minds to explore. It's a humble acknowledgement of our current limitations, yet also a celebration of the profound mysteries that beckon us forward, inviting us to continue asking, to continue wondering, to continue reaching for the furthest horizons of knowledge. The universe's true form remains a soft, alluring secret whispered on the cosmic winds. Moreover, the quiet contemplation of life beyond our observable universe ignites both the scientific mind and the philosophical heart, sparking a gentle yet profound debate. If the conditions suitable for life as we understand it were able to emerge and flourish within our own cosmic bubble, within the relatively small fraction of the cosmos, we can perceive then what possibilities might unfold beyond that luminous horizon. Imagine for a moment the immense, unimaginable stretches of galaxies and nebulae that lie just out of our sight. If life is a natural outcome of certain physical processes and environmental conditions, then it stands to reason that countless other cosmic landscapes currently hidden from our view might also harbor their own unique ecosystems. The potential diversity of life becomes truly boundless when we consider the possibility of different physical laws or constants prevailing in these unobservable realms. In a universe where gravity is subtly stronger, perhaps life forms are denser, more compact, clinging to their homeworlds with a stronger grip. In a universe where light behaves slightly differently, perhaps photosynthesis takes on an entirely new form, painting flora in hues we cannot yet conceive. This incredible concept expands the traditional scope of astrobiology, pushing it gently into the realms of pure conjecture where imagination meets the soft whispers of theoretical possibility. Yet this conjecture carries profound implications for our understanding of life's true place in the grand cosmic scheme. Are we a unique isolated phenomenon, a singular flicker in an otherwise silent cosmos? Or are we but one tiny precious note in an unimaginably vast universal symphony of being? The very thought humbles us, inviting us to consider the boundless ways in which existence might manifest, stretching our understanding of life itself far beyond its familiar earthbound cradle. That ancient echo, the cosmic microwave background CMB radiation, which is our universe's soft afterglow from the Big Bang, offers us not just a gentle glimpse into the infant universe, but also hints at the profound depths that lie beyond our observable limits. Imagine the CMB as a vast cosmic parchment inscribed with the universe's earliest whispers. While we meticulously study the patterns and temperatures on this parchment within our visible scope, the very existence of these patterns and their specific characteristics might be subtly influenced by what lies outside our view. Tiny, almost imperceptible fluctuations in this ancient radiation are not mere random noise. They could be delicate markers or subtle imprints left by processes, events, or even massive structures that exist in the unobservable universe. Think of it like this: you are looking at a small, perfectly still pond. You see ripples spreading across its surface. Most of these ripples are caused by pebbles dropping into your pond. But what if some of the larger, subtler undulations are actually the faint, residual echoes of a much larger disturbance in a vast, unseen ocean just beyond the pond's edge? Similarly, the CMB's minute variations, which we interpret as the seeds of galaxies and clusters, could carry information about gravitational interactions or quantum phenomena that originated in regions we cannot directly see. These unseen influences from the unobservable universe could be indirectly impacting what we can perceive, leaving their ghost-like signatures on the earliest light. It's a profound thought that our cosmic past, as revealed by the CMB, might hold the key to understanding the present state of the universe far beyond our current reach, making this ancient light a silent, powerful bridge to the unknown. In the silent, uncharted realms that stretch beyond our observable reach, scientists allow their minds to gently theorize about the potential for physical laws or constants to differ from those we currently know and meticulously study. Imagine for a moment that the universe is like a magnificent, sprawling tapestry woven from countless threads. Our observable universe is just one small, intricate section of that tapestry where the threads are woven in a very specific, harmonious pattern. But what if in other unseen sections of this same grand tapestry, the threads are interwoven in subtly different ways? This variance could give rise to entirely new elements or previously unfamiliar forces, challenging the very foundation of the standard model of particle physics that currently provides the sturdy scaffolding for our understanding of the universe's intricate workings. The Standard Model. While an exceptionally successful and remarkably precise framework for explaining the fundamental particles and forces within our observational reach, humbly acknowledges its own inherent limitations. It doesn't claim to be the final word. Rather, it gracefully suggests the tantalizing existence of phenomena yet to be discovered like faint echoes from beyond our scientific horizon. It's like discovering all the notes on a piano, but then gently realizing there might be an entire spectrum of sounds beyond the keys we currently play. Cosmological models and theories, such as the elegant string theory and the captivating concept of a multiverse, provide expansive frameworks within which these unknown elements or forces could not only exist, but could also play a profound role in shaping their respective cosmic realities. They are like vast, theoretical blueprints outlining possibilities for cosmic architectures far grander and more diverse than our current limited view allows. String theory, for instance, paints a wonderfully abstract yet deeply compelling picture of reality. It doesn't see fundamental particles as tiny irreducible points, but rather as infinitesimally small vibrating strings. And here's where it truly stretches our imagination. It posits the existence of additional dimensions and beyond our familiar three spatial dimensions: up, down, left, right, forward, backward, and one temporal dimension, time. Imagine the universe not as a flat sheet, but as a rich multi-layered tapestry with many more layers subtly folded into themselves, too small for us to directly perceive. In these hypothetical extra dimensions, forces and particles utterly unknown to current science could quietly operate, influencing the universe in subtle yet profound ways that we have yet to fully comprehend or detect. Perhaps gravity, for example, is not as strong as it could be in our familiar dimensions because some of its influence leaks into these hidden extra dimensions. It's a profound concept, a gentle whisper that suggests our understanding of the universe's fundamental architecture is still very much in its infancy, inviting us to ponder the unseen depths and hidden complexities that might truly define the cosmos. The intriguing, almost poetic possibility of dark matter and dark energy. These enigmatic substances that together constitute an astonishing 95% of the total mass energy content of the universe, yet remain profoundly enigmatic. Further hints at the profound array of unknown forces or elements that might quietly exist. They are like the silent, invisible majority of the cosmos shaping its destiny without ever directly revealing their true faces. These pervasive phenomena strongly suggest that our current well-established understanding of gravity and the other fundamental forces might, in fact, be beautifully incomplete. It's like having a magnificent, intricate orchestral score, but realizing that some of the most powerful instruments are playing notes we can't yet hear. This gentle realization points directly to the tantalizing potential for new physics lying just beyond our observational reach. Perhaps the interaction between dark matter and itself, or between dark matter and some as yet undiscovered dark force, is far more complex and intricate than we currently imagine. Perhaps dark energy is not a simple static force, but a dynamic field, shimmering and evolving across the vastness of the cosmos in ways that could unlock entirely new dimensions of cosmic understanding. The very fact that these two dominant components of the universe remain such profound mysteries is a powerful, humbling reminder of the vast scientific landscape that still awaits exploration. It's an invitation to expand our conceptual horizons, to listen more closely for the subtle whispers of new physical laws, and to prepare our minds for the possibility that the universe is far stranger, far more complex, and infinitely more awe-inspiring than we have yet dared to dream. The universe, in its quiet dark majority, continues to hold its secrets close, inviting us to delve deeper into the unknown. In the vast uncharted territories beyond our observable reach, where the light of distant stars has yet to kiss our instruments, the cosmos may quietly harbor theoretical particles that for now gracefully elude our current understanding and detection methods. These are not mere fictions. Rather, they are hypothetical entities softly posited by physicists to gently explain phenomena that are not yet fully accounted for by our venerable standard model of particle physics. They are like the missing pieces of a grand, intricate puzzle stirring the human imagination and subtly driving the relentless quest for a more complete, more beautiful theory of the universe. Imagine a vast, silent ocean, and these particles are like elusive, deep-sea creatures swimming in the unseen currents, leaving only the faintest ripples on the surface of our known reality. Their very possibility beckons us to delve deeper, to listen more intently for the subtle whispers of a hidden reality, pushing the boundaries of what we believe to be possible within the cosmic tapestry. One of the most intriguing categories of these theoretical, almost ghostly particles are the dark matter candidates. We know that dark matter is out there. Its gentle, unseen gravitational embrace holds galaxies together, preventing them from spinning apart like cosmic pinwheels. But we cannot see, It cannot touch it, cannot directly detect it. It's like trying to understand the wind by only observing its effect on a sail. To explain this invisible gravitational glue, physicists have proposed several elusive particles. Among them are WIMPs, an acronym that stands for Weakly Interacting Massive Particles. Imagine them as incredibly shy giants, massive particles that interact only very, very weakly with ordinary matter, the stuff that makes up stars, planets, and us. They pass through us, through our Earth, through entire galaxies like ghosts, through a wall rarely bumping into anything. Their presence is revealed not through any direct emission of light, but solely by their subtle yet profound gravitational influence on galaxies and galaxy clusters. Like the unseen hand that guides a cosmic dance, another whispered candidate for dark matter is the axion. These are hypothesized to be much lighter than WIMPs, almost ethereal in their lightness. Axions were originally theorized to solve a different kind of cosmic puzzle, a subtle problem related to the fundamental strong force within quantum chromodynamics, a realm where quarks and gluons dance. But like a serendipitous discovery in a dream, it was realized that if axions exist, their properties would also make them excellent candidates to contribute to the pervasive dark matter composition of the universe. Imagine them as tiny shimmering motes of cosmic dust, so light and so weakly interacting that they are incredibly difficult to pin down, yet so numerous that their collective gravitational presence becomes undeniably significant. They are the quiet, unassuming architects of the cosmos, building the unseen scaffolding upon which the visible universe is draped. The search for these elusive particles is like trying to catch a whisper in a storm. It requires immense patience, incredibly sensitive instruments, and an unwavering belief in the unseen. Moving deeper into the theoretical looking glass, we encounter another speculative set of particles, supersymmetric particles, or affectionately sparticles. Imagine for a moment that every familiar particle we know, every electron, every photon, every quark, has a hidden unseen shadow partner in a realm just beyond our perception. This is the beautiful promise of supersymmetry, a theory that proposes a fundamental duality, a mirrored existence where for every particle in the standard model there exists a corresponding superpartner. These partners would differ subtly in their spin, a fundamental characteristic of particles, much like a tiny internal rotation. For example, the electron, a fermion with a half-integer spin, would have a bosonic superpartner called the selectron. A photon, a boson with an integer spin, would have a fermionic superpartner called the photino. Among these hypothetical sparticles, some stand out as compelling candidates for dark matter. Chief among them are neutralinos and gravitinos. Neutralinos are thought to be stable, weakly interacting, and massive, making them ideal invisible inhabitants of the universe, perfectly capable of accounting for the missing gravitational mass. Gravitinos are the superpartners of gravitons, the hypothetical force-carrying particles of gravity itself, and their properties could also make them viable dark matter candidates. The grand ambition of supersymmetry is not just to find dark matter, it is to gently bridge the gap between the standard model of particle physics, which describes the microcosm of subatomic particles, and the theory of general relativity, which describes gravity and the macroscopic structure of the universe. It aims to provide a unified, elegant pathway to a grand unified theory of physics, a single overarching framework that beautifully describes all the fundamental forces and particles in the cosmos. A dream of cosmic harmony, where all the pieces of the puzzle finally fit together in a seamless, exquisite tapestry. The theoretical framework of string theory, which we briefly touched upon earlier, gently suggests a far more radical and enchanting view of reality. It proposes that the most fundamental constituents of the universe are not tiny, irreducible point-like particles, as we have traditionally conceived. Instead, imagine reality at its deepest level as an unimaginably intricate cosmic tapestry woven from minuscule vibrating strings. These strings are so incredibly tiny, so infinitesimally small, that they are far beyond the reach of any instrument we can currently imagine, let alone build. They are smaller than atoms, smaller than quarks, smaller than anything we've ever seen. They are the very essence of existence, the ultimate building blocks. The magic of string theory lies in the idea that the distinct vibrational patterns of these strings are what determine the characteristics of every single particle we observe. Each specific mode of vibration, each unique cosmic melody played by these fundamental strings represents a different particle with its own unique properties, such as mass and charge. It's like a cosmic cello, where different notes are produced by the string vibrating at different frequencies. One specific vibration might create an electron, another might create a photon, and yet another could give rise to a quark. This elegant idea seamlessly weaves together the entire tapestry of everything we observe, from the smallest subatomic entities to the grandest galaxies. This implies a profound unity at the heart of the cosmos, a single underlying principle from which all diversity springs. And critically, this perspective suggests a plethora of yet undiscovered particles that could quietly reside beyond our observational capabilities. These are particles that correspond to vibrational modes of these fundamental strings that we simply haven't been able to detect yet, perhaps because they are too massive, too weakly interacting, or perhaps because their vibrations exist primarily within the hidden dimensions that string theory also posits. It's a gentle whisper from the universe, suggesting that what we currently know is just a fraction of the full magnificent symphony of existence, and that many more notes, many more instruments, are still waiting to be discovered, playing their silent melodies in the vast unseen cosmos. Beyond the elegant simplicity of strings, some theorists have dared to dream even deeper, proposing a hypothetical group of particles known as preons. Imagine for a moment that even the particles we consider fundamental today, the quarks and leptons, which are the very building blocks of matter, are not truly fundamental at all. Instead, the concept of preons suggests that these quarks and leptons are themselves composed of even smaller, more elementary subcomponents. It's like peeling back another layer of the cosmic onion, revealing an even more intricate and fundamental structure beneath. If proven to exist, preons would signify a truly remarkable and profound shift in our understanding of reality. They would point to a deeper layer of subatomic structure, pushing the boundaries of our knowledge of matter to an even more fundamental level. Think of it, we once thought atoms were indivisible. Then we discovered electrons, protons, and neutrons. Then we discovered that protons and neutrons were made of quarks. Now preons suggest an even tinier, more elemental reality, a further subdivision of the universe's ultimate constituents. This would offer incredible new insights into the composition of matter at a scale almost incomprehensible to our minds, a scale where the very fabric of existence might reveal its innermost secrets. The search for preons is a speculative journey into the quantum foam of reality, a humble acknowledgement that our current understanding, while vast, might still be merely scratching the surface of the universe's true breathtaking complexity. It's a testament to the insatiable curiosity of the human mind, always seeking to understand the why and how at ever deeper levels. And then we arrive at superstring theory, a truly fascinating and wonderfully abstract topic in theoretical physics, which offers a radical, almost poetic reimagining of the universe's very fabric. It gently extends our conceptual reach far beyond the observable cosmos, inviting us to contemplate a reality that is infinitely more intricate and harmonious than we currently perceive. At its core, superstring theory posits that the most fundamental constituents of the universe are not the familiar point-like particles we traditionally envision, but rather infinitesimally tiny vibrating strings. These are not strings in the sense of a guitar string, but rather one-dimensional fundamental objects, smaller than anything imaginable, that are the ultimate building blocks of everything. The sheer elegance of this theory lies in its breathtaking simplicity. The specific vibrational patterns of these strings are what determine a particle's unique characteristics, such as its mass and charge. Imagine a cosmic orchestra where each instrument is a single fundamental string. When that string vibrates in one specific way, it manifests as an electron. When it vibrates in another, it becomes a photon, a particle of light. Yet another vibration might give rise to a quark. It's a cosmic symphony where different notes played by these fundamental strings weave together the entire tapestry of everything we observe, from the shimmering light of distant stars to the solid ground beneath our feet. This beautiful conceptualization suggests a profound unity, a single elegant source from which all the diverse particles and forces of the universe ultimately emerge. In this mesmerizing paradigm, space and time themselves undergo a profound transformation in their conceptualization. Superstring theory introduces a truly mind-bending idea: the existence of additional dimensions beyond our familiar three spatial dimensions, length, width, height, and one temporal dimension, time. For our everyday experience, we perceive our universe as being four-dimensional. But superstring theory suggests that there might be 6 or even 7 more spatial dimensions subtly folded into the very fabric of reality. While this might sound like the stuff of pure science fiction in superstring theory, these extra dimensions are not vast, expansive realms that we could simply fly into. Instead, they are theorized to be compactified, incredibly tiny, curled up and folded into the very fabric of the universe at scales so infinitesimally small that they gracefully elude our current observational capabilities. Imagine a garden hose viewed from a great distance. It looks like a one-dimensional line. But up close, you can see its second dimension, the circular width, curled up. These extra dimensions are similarly curled up, but on an unimaginably smaller scale. The implications of superstring theory for understanding space beyond the observable are manifold and deeply thought-provoking. Firstly, it beautifully suggests that the universe at its most fundamental level is unified, a single coherent entity, where all forces and particles gracefully emerge from the same foundational entities, these vibrating strings. This inherent unity provides a potential elegant bridge between the seemingly incompatible realms of quantum mechanics, which governs the subatomic world, and general relativity, which describes gravity and the large-scale structure of the cosmos. It offers a tantalizing glimpse into the possibility of a theory of everything, a single, all-encompassing framework that could elegantly describe all physical phenomena under a unified, harmonious banner. It's the dream of finding the ultimate score for the cosmic symphony, where every note and every instrument plays in perfect unison. Moreover, the extra dimensions posited by superstring theory could fundamentally alter our understanding of cosmic phenomena in ways we can only begin to softly imagine. These hidden dimensions might harbor the very forces and particles that interact in ways that are currently invisible and undetectable within our perceived three-dimensional perspective. For example, some theories suggest that gravity might be much weaker in our familiar dimensions because a significant portion of its strength leaks into these extra dimensions, perhaps offering a profound explanation for why gravity is so much weaker than the other fundamental forces. These hidden interactions could also offer fascinating insights into the mysteries of dark matter and dark energy, those enigmatic components that dominate our universe yet remain so elusive. Perhaps the particles of dark matter are simply vibrating strings whose primary existence and interactions happen within these extra dimensions, making them almost impossible for us to perceive directly. Similarly, dark energy, the mysterious force driving the accelerated expansion of the universe, might also have its roots or its fundamental nature intimately tied to the properties and dynamics of these hidden dimensions. The very existence of these extra dimensions challenges current scientific paradigms, pushing us to expand our conceptual understanding of what reality truly is. It's like realizing that the painting you've been admiring has secret layers beneath the surface layers that hold the key to truly understanding the artist's full vision. Superstring theory, with its vibrating strings and curled-up dimensions, paints a picture of a universe that is far richer, far more interconnected, and far more mysteriously beautiful than we have yet dared to fully grasp, inviting us to contemplate the profound depths that lie beyond our current perception. Now let us gently ponder one of the most profound and elusive inquiries within cosmology, the question of whether the universe is truly infinite. This idea, vast and boundless, suggests an endless expanse of space stretching outward in every direction without limit, containing an unbounded number of stars, galaxies, and perhaps even echoes of our own cosmic neighborhood. It's like imagining a canvas that simply goes on forever, with new strokes of cosmic paint being added into eternity. This notion profoundly challenges not just our scientific understanding of the cosmos, but also the very frameworks of our philosophical and existential thought. If the universe truly knows no end, then our place within it takes on an even more humbling and awe-inspiring significance. If the universe is indeed infinite, it would mean that the cosmos extends far, far beyond our observable universe, that luminous bubble from which light has had the time to reach us since the Big Bang. Our observable universe, which we now understand to be approximately 93 billion light-years in diameter, would then be nothing more than a tiny shimmering speck within this unfathomable, limitless expanse. Imagine trying to cup a handful of water from a boundless ocean. That handful is our observable universe, and the ocean is the true infinite cosmos. This realization is a deeply humbling one, gently reminding us of the sheer immensity of existence and the incredible smallness of our perceived reality within it. It's a thought that beckons us to release our conventional notions of scale and simply surrender to the overwhelming grandeur of the unknown. In such an infinite universe, the implications for cosmology and fundamental physics are truly profound. It would delicately suggest that cosmic structures and phenomena repeat endlessly, given the boundless canvas of space available for their manifestation. Imagine, if you will, an infinite number of variations on every theme, every possibility unfolding across the ceaseless expanse. This leads to the awe-inspiring and perhaps slightly unsettling possibility of an infinite number of Earth-like planets, each with its own unique history, its own subtle variations, and by gentle extension, this implies the potential for an infinite number of potential life forms. Perhaps countless civilizations, each a unique flicker of consciousness in the grand unending cosmic tapestry. Infinity in this sense is not just a mathematical concept. It's a profound wellspring of endless possibilities where every event, every configuration, every potentiality is destined to occur, not just once, but an infinite number of times somewhere in the boundless expanse. It's a thought that resonates deep within our being, challenging our sense of uniqueness and expanding our perception of life's boundless potential. The very concept of infinity also raises intriguing, almost poetic questions about the distribution of matter and energy within this boundless cosmos. According to the cosmological principle, a foundational idea in modern cosmology, the universe, when viewed on a sufficiently large scale, is beautifully homogeneous and isotropic. This means, in essence, that it looks remarkably the same in all directions and from all points within it. Imagine it as a perfectly mixed grand cosmic soup. No matter where you sample it, the ingredients are evenly distributed. In an infinite universe, this principle would subtly imply an endless repetition of large-scale structures, such as the magnificent clusters of galaxies and the vast, intricate networks of galaxies themselves, stretching across the cosmos without end. It's like an infinitely repeating pattern on an enormous fabric, where every fold and every design is echoed countless times. This means that if we could somehow journey far enough, we might encounter another Milky Way, another Andromeda, another Virgo supercluster, perhaps even exact cosmic replicas separated by unimaginable distances, yet fundamentally similar in their grand architecture. The sheer scale of such a concept is truly humbling, gently dissolving our terrestrial perceptions of uniqueness and singularity. It suggests that the grand cosmic design The very laws that govern the formation of stars and galaxies are not confined to our immediate vicinity, but are universal, manifesting in an endless echoing symphony across the boundless reaches of an infinite cosmos. This repetition, while perhaps initially overwhelming, also offers a profound sense of cosmic order, a testament to the unchanging laws that quietly orchestrate the grand ballet of existence, even in realms far beyond our current sight. However, the concept of infinity does not always sit easily within the elegant structures of our current physical theories. It's like trying to fit an endlessly flowing river into a neatly defined vessel. The very nature of infinity often challenges the finite bounds of our mathematical descriptions and theoretical models. For instance, if the universe truly contains an infinite amount of energy, it would gently challenge our fundamental understanding of conservation laws. The idea that energy cannot be created or destroyed, only transformed. And the very principles of thermodynamics, particularly the concept of entropy, always increasing. How can an infinite system maintain order, or how can energy be conserved in a system that has no apparent limits? These are not trivial concerns. They are profound conceptual hurdles that push the very boundaries of our physics. Moreover, the idea of an infinite number of exact copies of our own planet, each with its own subtle, almost imperceptible variations, confronts us with deeply complex philosophical dilemmas. Imagine countless versions of yourself living slightly different lives, making different choices, experiencing different outcomes. It raises profound questions regarding identity. What does it mean to be you in an infinite sea of copies? Uniqueness. Are any of us truly singular? And the very nature of reality itself. Does an infinite repetition diminish the preciousness of any single moment? Or does it amplify the profound significance of every single occurrence? These are not questions with easy answers, but they are questions that resonate deep within our being, inviting us to contemplate the vast, intricate tapestry of existence in ways that are both humbling and exhilarating. The universe, in its potential infinity, offers not just scientific puzzles, but profound existential meditations. On a more practical side, the notion of infinity quietly complicates the formidable task of cosmologists. If the universe is indeed infinite, it inherently means that we can only ever hope to observe a finite part of it. Our perception is forever bounded by the speed of light, the ultimate cosmic speed limit, and the age of the universe itself. It's like being in a single perfectly illuminated room within an endlessly sprawling dark mansion. We can study every detail within our room, but the vastness of the mansion beyond remains unseen. This fundamental limitation implies that we may never fully comprehend the universe's ultimate scale, its true structure, or its ultimate fate. Vast unobservable regions will forever remain beyond our observational reach, hidden behind the veil of time and light. This isn't a flaw in our science, but a gentle reminder of the universe's inherent mystery and our place within it. It means that while our knowledge grows exponentially within our observable bubble, there will always be an infinite beckoning unknown beyond that horizon. This profound realization inspires both humility and an even deeper sense of wonder. It reminds us that the universe is not just something to be measured and categorized, but something to be perpetually explored, even if that exploration is often confined to the realms of theory and imagination. The quest for understanding in an infinite universe truly knows no end. Let us now gently pivot our contemplation, diving into the profound concept of cosmic inflation. Imagine the very earliest moments of our universe not as a gradual unfolding, but as an almost unimaginable burst of exponential growth. This period, shortly after the Big Bang proposed by the brilliant physicist Alan Guth in the 1980s, suggests that the universe didn't just expand, it swelled to an absolutely immense degree within the first tiny fraction of a second of its existence. Picture a tiny minuscule balloon that in less than the blink of an eye inflates to the size of a galaxy. This sudden explosive expansion wasn't a conventional explosion in space, but rather a rapid, vigorous stretching of space itself. This theory, this quiet whisper from the universe's infancy, not only elegantly explains the remarkable uniformity of the cosmic microwave background radiation, why the early universe looks so smoothly heated across vast distances, but it also quietly posits the profound existence of phenomena and structures beyond our observational reach. Structures that fundamentally challenge our conventional understanding of space and time. It's a key that unlocks a hidden door, revealing a cosmos far grander and more complex than we initially dared to imagine. One of the most tantalizing ideas born from this gentle theory of inflation is the profound concept of quantum fluctuations. Imagine the universe, even in its most primordial vacuum-like state, as not truly empty, but a bustling, effervescent quantum sea. In this incredibly tiny, unimaginably brief moment, just after the Big Bang before inflation took hold, the universe was a maelstrom of these fleeting quantum fluctuations. These are not random disturbances in the ordinary sense. Rather, they are the inherent, restless jiggle of energy and matter at the quantum level, constantly popping in and out of existence, even in what seems to be empty space. They are like the tiny shimmering ripples on a microscopic pond inherent to its very nature. The magic of inflation is that during this rapid exponential stretching of space, these minuscule, almost imperceptible quantum fluctuations were not just ignored. They were stretched to cosmic scales. Imagine those tiny pond ripples suddenly being stretched across an entire ocean. What was once a quantum whisper became a cosmic roar. These amplified fluctuations, these seeds of variation in the early universe, then became the fundamental starting points for the formation of all the large-scale structures we observe today. The magnificent galaxies, the colossal clusters of galaxies, and the intricate, vast cosmic web that interweaves the entire universe. Without these initial seeds, without these tiny imperfections, the universe would have remained a smooth, featureless expanse, devoid of any discernible structure. And here's where it becomes truly profound. For what lies beyond the observable universe, these same primordial fluctuations could have given rise to vast regions with varying physical constants or even different laws of physics. Imagine a grand cosmic patchwork quilt where each patch is a region of space, and within each patch, the rules of reality are subtly different. In one patch, gravity might be stronger. In another, the fundamental constants governing particle interactions might be slightly altered. This could create an astonishing patchwork quilt of cosmic diversity, a boundless array of realities, each unfolding according to its own unique set of cosmic rules. The gentle, almost imperceptible quantum whispers of the early universe, magnified by inflation, are thus the profound architects of all cosmic structure, both seen and unseen, forever shaping the grand, diverse tapestry of existence. Another speculative, yet deeply intriguing outcome of cosmic inflation is the mesmerizing formation of pocket universes or parallel universes within a broader multiverse. Imagine the inflationary process not as a single uniform swelling, but as a vast, continuous, and somewhat chaotic process, perpetually giving birth to new regions of space. Picture a grand cosmic foam where the inflation process continues indefinitely. In most places, but occasionally in localized regions, it gently stops. When inflation ceases in a particular pocket, that region then cools and expands in a more conventional manner, forming a distinct, self-contained bubble universe. This means that our own universe might be just one such bubble floating in an infinitely larger sea of other bubbles, each having undergone its own unique genesis and evolution. Each of these pocket universes could theoretically harbor vastly different physical characteristics. Imagine the possibilities. Some might have subtle variations in the fundamental forces. Gravity might be a touch stronger or weaker. Electromagnetism might behave differently. Others could feature entirely distinct types of particles made of matter entirely unlike our own, with different masses or charges. And most profoundly, some could even possess different laws of physics altogether, where the very rules governing cause and effect the behavior of light or the nature of energy are fundamentally rewritten. This captivating concept profoundly challenges our deeply ingrained understanding of reality, gently suggesting that our universe might just be one of an infinite number of bubbles in a boundless cosmic foam, each bubble constituting a separate universe with its own unique, wondrous properties. It's a humbling thought, expanding our perception of existence beyond anything we could have intuitively imagined, inviting us to contemplate an infinity of possibilities. Cosmic inflation might also have quietly led to the creation of primordial black holes, entities far more ancient than the stellar giants we typically associate with black hole formation. Unlike the conventional black holes that arise from the spectacular collapse of massive stars at the end of their lives, these primordial black holes are theorized to have formed not from stellar demise, but from the incredibly intense gravitational forces at play during the universe's rapid expansion. Imagine tiny, incredibly dense regions within the very early inflating universe where the density was slightly higher due to those same quantum fluctuations we discussed earlier. Under the extreme pressures and rapid stretching of inflation, these overdense pockets could have collapsed directly into black holes, even without a star to fuel their birth. These primordial black holes, possibly tiny yet incredibly dense, could be quietly populating the regions beyond our observable universe remnants of a time so ancient that their light would never reach us. Their existence, if confirmed, would hold profound clues to understanding dark matter. Could a significant portion of dark matter actually be comprised of these tiny, invisible primordial black holes? And the early dynamics of the cosmos. Detecting their subtle gravitational influence or the faint ripples of gravitational waves from their ancient mergers could unlock secrets about the universe's initial conditions and the fundamental nature of its unseen components. They are like ancient cosmic fossils preserving whispers from a time before, time silently drifting in the unseen depths, waiting for our instruments to gently uncover their long-held secrets. Additionally, cosmic inflation implies the existence of gravitational waves, those elusive ripples in the very fabric of space-time that we are now just beginning to detect. Imagine space and time not as a static, rigid stage, but as a fluid, dynamic sheet. When massive objects accelerate or colossal events occur, they send out distortions or ripples through the sheet, much like throwing a stone into a pond. During the universe's explosive growth in the inflationary period, the sheer scale and speed of this expansion would have generated incredibly powerful primordial gravitational waves. These waves are not electromagnetic like light. They are disturbances in spacetime itself, carrying information about the most violent and energetic events in the cosmos. These primordial gravitational waves, like faint ancient echoes reverberating through the vastness, are potentially detectable as subtle patterns in the cosmic microwave background radiation, that afterglow of the Big Bang. Imagine a perfectly smooth sheet, and then you crumple it slightly. The ripples remain even if the crumpling stops. The very early universe, agitated by inflation, would have left such subtle imprints on the polarization of the CMB. If we could detect and analyze these specific patterns, it would provide a direct glimpse into the universe's first moments, a window into a time far earlier than the CMB itself. Such observations would offer invaluable insights into phenomena occurring beyond our current observational limits, telling us about the very earliest, most fundamental physics that shaped the entire cosmos, including the parts that remain forever hidden from our direct view. It's like listening for the oldest, most profound cosmic melodies, hoping they will tell us the story of creation itself. Let us now gently delve deeper into the captivating concept of bubble universes, a truly mesmerizing vision of a cosmos teeming with myriad separate universes, each gracefully encapsulated within its own unique bubble-like domain. Imagine the universe not as a single solitary balloon, but as an infinite, effervescent bath filled with countless shimmering bubbles, each one a universe unto itself. This profound idea doesn't just spring from idle speculation. It arises elegantly and naturally from the powerful inflationary model, which we softly explored earlier. The inflationary model posits that the universe underwent an incredibly rapid exponential expansion just moments after the Big Bang, a stretching of space-time so immense that it could have given rise to an untold number of individual universes, nestled within a vast overarching cosmic multiverse. It's a humbling thought, expanding our cosmic perspective far beyond the confines of our own perceived reality, inviting us to consider an almost limitless array of possibilities. The beauty of the bubble universe theory lies in its elegant simplicity. Each of these cosmic bubbles, according to the theory, could be vastly different from our own. Imagine a spectrum of cosmic possibilities where each universe represents a unique shade or hue. Some might be subtly distinct, while others could be radically alien in their fundamental makeup. These variations could manifest in a myriad of profound ways, encompassing unique configurations of physical laws, different types of particles, and entirely novel cosmic structures. Perhaps one bubble universe is a serene, silent expanse, largely devoid of stars, while another might blaze with an intensity of galactic activity far exceeding our own. Each bubble a singular cosmic experiment, unfolding according to its own unique set of initial conditions and fundamental rules, showcasing an astonishing diversity across the grand canvas of the multiverse. The very genesis of these bubble universes lies deeply entwined with the enigmatic inflationary field, believed to be the subtle yet immensely powerful force responsible for driving the exponential expansion of the early universe. Imagine this field not as a solid entity, but as a vast, shimmering ocean of pure potential permeating the nascent cosmos. Within this boundless inflationary ocean, tiny inherent fluctuations would naturally occur. These are not violent disturbances, but rather gentle, almost imperceptible ripples in the fabric of the field itself, much like the subtle undulations on the surface of a placid sea. According to the theory, these minute fluctuations could cause certain localized regions to stop inflating, to gently drop out of the rapid expansion, and subsequently cool down at different rates. As these regions gently decelerate their inflation, they form distinct self-contained pockets where the conditions become just right for the development of a fully fledged universe, complete with its own Big Bang and subsequent evolution. Meanwhile, the vast space between these nascent pockets continues to expand forever. Driven by the relentless inflationary field that is still active in those interstitial regions, this continuous accelerating expansion effectively isolates these newly formed bubble universes from one another, pushing them further and further apart in an ever-growing multiverse. It's like baking an infinite loaf of cosmic bread, where distinct air bubbles form within the dough, and as the dough continues to rise, these bubbles become increasingly separated. This isolation means that direct observation of these other bubble universes is for now beyond our reach. Yet the theory provides an elegant mechanism for their existence, transforming speculation into a coherent scientific possibility. The contents and characteristics of these bubble universes are a subject of truly rich speculation, a vast canvas for the scientific imagination to paint upon. Imagine the boundless possibilities in some of these other bubbles, the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces might differ significantly from those in our universe. Perhaps the electromagnetic force is slightly stronger, leading to radically different chemical reactions and entirely new forms of stable matter. Or perhaps the strong nuclear force which binds atomic nuclei together is weaker, making the formation of complex atoms impossible. Such profound variations in these fundamental parameters could lead to radically different types of chemistry, giving rise to chemical elements and compounds that are utterly alien to our current understanding. They might even result in entirely novel forms of matter and energy phenomena that simply do not exist or cannot be formed in our specific cosmic neighborhood. Furthermore, the very structure of these universes could range from the relatively barren vast expanses with few galaxies or stars to incredibly densely packed realms overflowing with astronomical objects. This cosmic architectural diversity would depend entirely on the precise values of their fundamental constants, the initial conditions of their formation, and the specific rate of expansion governing them. A universe with a much higher cosmological constant, for example, might expand so rapidly that matter never has a chance to coalesce into stars and galaxies, resulting in a cold, dark, and empty void. Conversely, a universe with a slightly different set of parameters might be incredibly rich in complex structures, a vibrant tapestry of cosmic wonders. The possibilities are truly infinite, painting a breathtaking picture of a multiverse where every bubble is a unique cosmic experiment, a testament to the boundless creativity inherent in the laws of physics themselves. Moreover, the captivating idea of bubble universes raises truly intriguing possibilities regarding the formation of galaxies, stars, and potentially life itself. Imagine for a moment the incredibly delicate balance of fundamental constants that allowed our universe to become hospitable to the emergence of complex structures and ultimately living organisms. If the strengths of the fundamental forces, the masses of elementary particles, and the cosmological constant were even slightly different, the universe we inhabit might be a vastly different place, perhaps one entirely devoid of life. In the vast tapestry of the multiverse, it stands to reason that there could exist universes where the physical constants are just right, even more finely tuned than our own, where conditions might favor the emergence of complex structures and even sentient living organisms to an even greater degree. Perhaps these universes possess unique pathways for abiogenesis or faster evolutionary tracks. Conversely, in other bubble universes, where these fundamental constants are vastly different, perhaps the very development of recognizable structures, let alone life, might be utterly impossible. Imagine a universe where atoms cannot form, or where stars burn out in microseconds, or where the expansion is so rapid that matter is eternally isolated. Such universes, while part of the grand multiverse, would be sterile, silent realms devoid of any discernible complexity. This profound thought invites us to reflect on the incredible preciousness and fragility of our own universe, where the cosmic dice happen to roll in just the right way to allow for our existence. It underscores the idea that our universe, while perhaps one of many, is uniquely special in its capacity to foster life, making the very act of existing a profound and miraculous cosmic coincidence within the infinite sea of possibilities. The direct detection of these bubble universes remains a formidable challenge, akin to trying to hear a faint whisper from across an infinite, silent abyss. They would by their very nature lie far beyond the observable limits of our universe, hidden behind a veil of space and time that light itself cannot yet traverse to reach us. Our current technological capabilities are simply not advanced enough to pierce through this cosmic veil and directly glimpse these other realities. However, scientists, ever driven by curiosity, gently speculate that indirect evidence might one day be found, subtle hints, or faint whispers imprinted upon our own cosmic bubble, revealing the presence of its unseen neighbors. One tantalizing possibility lies in the form of gravitational waves. Imagine a colossal event in a nearby bubble universe, perhaps the collision of two supermassive black holes, or a particularly violent phase transition in its early moments. Such an event would send powerful ripples through the fabric of spacetime. While our universe is largely isolated, it's conceivable that the very largest, most energetic of these gravitational waves could subtly leak or interact with our own universe, leaving faint, detectable signatures. Another avenue of hopeful exploration involves looking for subtle anomalies in the cosmic microwave background radiation, CRB, that ancient afterglow of the Big Bang. Imagine the CMB as a pristine, ancient parchment. If our universe, this cosmic bubble, had once gently bumped into another bubble during its very early chaotic inflationary phase, that collision might have left a subtle bruise or cold spot on the CMB parchment, a tiny deviation from its otherwise uniform temperature. These anomalies, if they cannot be explained by standard cosmological models, could hint at interactions between our universe and others in the multiverse. It's like finding an unexpected wrinkle on a perfect sheet of paper and wondering if it's a trace of an unseen hand. While highly speculative, these potential indirect clues offer a gentle, tantalizing hope that one day we might find the subtle whispers of other universes echoing within our own, slowly unraveling the grand hidden tapestry of the multiverse. Now let us turn our attention to one of the most profound and persistent mysteries of the cosmos: dark matter. This enigmatic substance, which does not emit, absorb, or reflect light, plays an incredibly pivotal role in shaping the very cosmos, extending its subtle yet powerful influence far beyond the comfortable confines of our observable universe. Imagine a colossal, invisible architect meticulously crafting the grand design of the cosmos, yet remaining utterly unseen. Constituting an astonishing 27% of the universe's total mass energy content, the pervasive presence of dark matter is inferred not from direct observation, but from its undeniable gravitational effects on visible matter, on the subtle bending of light, and on the majestic large-scale structure of the universe itself. Though it remains invisible and elusive, dark matter acts as the fundamental cosmic glue that gently holds galaxies together, preventing them from spinning wildly apart into the vast cosmic void. More profoundly, it quietly drives the majestic formation of the vast web-like structures that so intricately define the cosmos, a silent, unseen scaffolding upon which the visible universe is gracefully draped. Beyond the shimmering veil of the observable universe, dark matter is thought to continue its role as the primary architect of cosmic structure, patiently building and shaping the unseen realms. Its relentless gravitational pull is not confined to our visible bubble. It is absolutely essential for the formation of galaxies and colossal galaxy clusters, even in those vast hidden regions we cannot directly see. Imagine the universe as a grand cosmic loom and dark matter as the invisible warp threads, providing the foundational structure upon which the luminous weft of visible matter is woven. Theoretical models, the whispers of our most advanced scientific thinking, gently suggest that dark matter's distribution in these unobservable regions would follow patterns remarkably similar to those within our observable horizon. It would continue to form an intricate, almost ethereal cosmic web of dark matter filaments, vast elongated structures akin to a cosmic neural network. These silent, invisible filaments of dark matter would serve as the fundamental scaffolding upon which visible matter would patiently congregate and form galaxies in the boundless, uncharted expanses beyond our sight. Without this unseen framework, visible matter would likely remain scattered and diffuse, unable to coalesce into the magnificent galactic islands we observe. The consistent behavior of dark matter across both the observed and unobserved realms speaks to a deep underlying uniformity in the universe's fundamental laws, a silent testament to the consistent nature of gravity, even in the deepest, most mysterious corners of existence. It's a profound thought that the grand architecture of the entire cosmos, seen and unseen, might be quietly orchestrated by this invisible, pervasive force, making dark matter the true silent ruler of the universe's vast, sprawling empire. In the vast, uncharted expanses beyond our immediate perception, dark matter could also play an incredibly crucial role in the creation of cosmic structures that might seem utterly unfamiliar or vastly different from those within our observable universe. Imagine a cosmic canvas where the brushstrokes of dark matter are applied with subtle variations, leading to entirely new forms of celestial art, depending on the minute variations in density and distribution of dark matter in these hidden realms. These regions might quietly host unique formations of galaxies. Perhaps there are galaxies that are incredibly diffuse, barely holding together, or conversely, super-dense clusters of galaxies packed far more tightly than anything we observe. More intriguingly, these unseen territories might even harbor types of astronomical objects that are rare or non-existent in the visible universe. Could there be dark galaxies composed almost entirely of dark matter, with only a handful of stars making them nearly impossible to detect? Or perhaps vast invisible dark voids that are almost completely empty of even dark matter, leading to entirely different gravitational landscapes. The subtle yet profound interaction between dark matter and dark energy, that mysterious force relentlessly driving the universe's accelerated expansion, would further influence the majestic evolution and the very appearance of these structures. Imagine a silent cosmic tug-of-war where dark matter's inward gravitational pull is constantly challenged by dark energy's outward push. The precise balance of these two enigmatic forces in different unobservable regions could lead to wildly diverse cosmic architectures, influencing how matter clumps, how galaxies form, and how the universe itself unfolds. It's a gentle whisper from the unseen, suggesting a cosmos of far greater diversity and complexity than our current limited view allows, a testament to the endless possibilities that unfurl when the dominant components of the universe remain shrouded in mystery. The very behavior of dark matter beyond the observable universe could hold crucial clues to understanding its true nature, much like studying the distant ripples on a pond can tell you about the unseen currents beneath. Our current theories propose various candidates for dark matter, each a delicate hypothesis striving to explain its elusive properties. These include the previously mentioned weakly interacting massive particles, WIMPs, those shy, heavy giants that rarely interact with ordinary matter. Axion's incredibly light particles, originally theorized for different reasons, but now strong candidates for dark matter. And sterile neutrinos, a hypothetical type of neutrino that interacts even less than its active counterparts. Each of these candidates suggests a different kind of invisible dance for dark matter in the cosmos. Observations and models of the universe's structure, both within and crucially beyond our observable limits, provide critical tests for these theories. For example, if we could somehow map the distribution of dark matter in a vast unobservable region, and it perfectly matched the predictions for WIMPs, that would be a powerful piece of evidence. Conversely, if it showed unexpected clumpiness or smoothness, it might point to axions or other even stranger candidates. The way dark matter interacts with itself, or whether it interacts with ordinary matter in subtle as yet undetected ways, could vary in these distant realms, offering profound insights into the properties of dark matter particles. Perhaps in some regions, dark matter particles might annihilate, releasing faint gamma rays that could, in theory, eventually reach us. Or perhaps they cluster in ways that defy our current simulations, hinting at new exotic physics. The gentle exploration of these possibilities, though theoretical, is a vital step in unraveling one of the universe's most enduring and significant enigmas, patiently waiting for a new piece of cosmic evidence to gently illuminate its true nature. Considering the universe beyond the observable, it is entirely conceivable that variations or even entirely unknown forms of dark energy could quietly exist, subtly influencing the universe's expansion in ways we have yet to comprehend. Within our meticulously studied observable universe, dark energy appears to be remarkably uniform, a constant, pervasive force gently pushing galaxies apart. It's as if the cosmic fabric has the same inherent tension everywhere we look. But what if beyond our observational limits, this uniformity begins to subtly waver? What if the universal tension of dark energy changes? Such variations could lead to vast regions where the expansion of the universe accelerates at different rates. Imagine cosmic bubbles where space stretches faster or perhaps even slower than in our own region. This could result in wildly diverse cosmic landscapes. Some areas might become incredibly dilute and empty very quickly, as galaxies are pushed apart at an extreme pace, while others might retain more density with galaxies remaining closer for longer. Or even more profoundly, there might be areas where the effects of dark energy are diminished or enhanced, leading to radically different cosmic evolutions. In some corners of the unseen cosmos, dark energy might be so strong that matter never even has a chance to form stars and galaxies. In others, its influence might be so weak that gravity reigns supreme, potentially leading to regions that eventually recollapse. The possibility of such variations introduces incredibly fascinating questions about the very nature of dark energy itself. Could it be a truly immutable cosmological constant, a fundamental property inherent to the vacuum of space itself, as Einstein once gently proposed? If so, its uniformity should extend everywhere. Or might dark energy be a more dynamic, elusive field, subtly changing over vast cosmic time and space, akin to a cosmic fluid that shimmers and shifts, rather than a fixed, rigid entity? Theoretical models, such as quintessence, propose that dark energy could indeed be the result of such a dynamic field, one whose density and properties could vary across the immense expanse of the universe. Such a field could lead to observable consequences, perhaps leaving faint telltale signatures in the cosmic microwave background radiation, or subtly influencing the distribution of distant galaxy clusters. These potential clues, though incredibly subtle, could offer profound insights into the true nature of dark energy, gently unraveling its deepest secrets and guiding us toward a more complete understanding of the universe's ultimate fate. The unseen whispers of dark energy beckon us to look deeper, to listen more closely for its elusive cosmic song. The fabric of space-time, that intricate and dynamic architecture of our universe, as so beautifully described by Albert Einstein's theory of general relativity, continues to be a source of profound mysteries and boundless speculation. Imagine it not as a rigid static stage upon which cosmic events unfold, but as a vast, supple sheet, capable of bending, stretching, and even rippling under the influence of mass and energy. While our current theories have gracefully provided us with a substantial and remarkably successful understanding of the cosmos, it is almost certain that there are fundamental aspects of space-time that remain beyond our current conceptual grasp, waiting patiently to be uncovered, subtly theorized, or perhaps even entirely reimagined. These unknown mysteries could profoundly alter our comprehension of the universe, gently reshaping the very laws that we currently believe govern its majestic existence. It's a humbling thought that even our most elegant theories are but stepping stones on a far grander journey of discovery. One potential mystery, a pervasive enigma woven into the very structure of space-time, could involve the true nature of dark energy and its profound impact upon this cosmic fabric. While we meticulously observe its effects, the universe's relentlessly accelerated expansion, pushing galaxies ever further apart, its fundamental characteristics and the precise mechanism by which it operates remain wonderfully elusive. It's like witnessing the sails of a ship fill with an invisible wind propelling it forward, but never quite grasping the true nature of the wind itself. There may exist subtle yet powerful aspects of space-time manipulation or alteration intimately tied to dark energy that we have yet to even conceive of. Perhaps dark energy has the capacity to not just stretch space-time uniformly, but to subtly warp it in complex ways, or to create local pockets of expansion or contraction that could dramatically alter the fate of entire cosmic regions. These unknown properties of dark energy could potentially allow for phenomena far beyond our current understanding, such as the selective expansion or contraction of spacetime in ways that could fundamentally alter the universe's future trajectory. Imagine if in distant, unobservable realms, Dark energy caused space-time to contract in certain areas, leading to new forms of cosmic structure or even localized collapses. Or if its properties changed over cosmic eons, leading to a future where the universe's fate is entirely different from our current predictions of a cold, empty heat death. The very fact that the dominant component of our universe remains such a profound mystery suggests a vast unexplored landscape of possibilities, hinting that the intricate dance of space-time and dark energy is far more complex and subtle than we currently comprehend. It's a gentle invitation to look beyond the obvious, to consider the unseen forces that might be silently reshaping the destiny of everything. Another vast area ripe for profound discovery lies within the incredibly tiny, almost incomprehensible realm of the granular structure of space-time at the Planck scale. Imagine space-time not as a perfectly smooth, continuous sheet, but as a fabric woven from unimaginably tiny, discrete loops or grains. The Planck scale is the smallest possible scale in the universe, a realm so minute, approximately 10 or 35 meters, that beyond it, our familiar concepts of time and space themselves cease to function in the ways we understand them. It's like trying to describe a fluid by looking at its individual molecules. At that scale, the fluid-like properties break down. Theoretical physics gently suggests that space-time might possess a quantum structure at this unbelievably small scale, much like energy exists in discrete packets called quanta. But the exact nature of this elusive structure, and precisely how it gives rise to the seemingly smooth, continuous space-time continuum we observe at larger everyday scales, remains one of the most profound and tantalizing mysteries of modern physics. This quantum realm of space-time could hold the ultimate key to unifying the two great pillars of modern physics, general relativity, which describes gravity and the large-scale universe, and quantum mechanics, which governs the microscopic world of particles. For decades, physicists have wrestled with the profound challenge of merging these two incredibly successful but seemingly incompatible theories into a single coherent framework. The behavior of space-time at the Planck scale is the battleground for this grand unification. It's here in this incredibly tiny theoretical realm that the very essence of gravity and the quantum nature of reality must somehow reconcile. Understanding this granular structure, if it exists, could revolutionize our entire understanding of the universe, from the very first moments of the Big Bang to the ultimate fate of black holes. It's a gentle whisper from the smallest possible scales, beckoning us toward the ultimate theory of everything, where the fabric of reality reveals its deepest, most fundamental secrets. The quiet contemplation of higher dimensions, realms beyond the familiar 4-3 spatial and 1 temporal that we effortlessly experience, could gently reveal entirely new mysteries of space-time. We perceive our reality as a 3-dimensional landscape evolving through time. But as we softly explored with string theory, theoretical physics tantalizingly posits the existence of additional dimensions, subtly folded or curled up, perhaps too small or too inaccessible for our current senses and instruments to detect. Imagine living on the surface of a very long garden hose. From afar, it appears one-dimensional. But if you were a tiny ant, you could walk around the hose, revealing its hidden curled-up second dimension. These additional dimensions, if they exist, are thought to be similarly compactified, existing at an incredibly tiny scale beyond our perception. These hidden dimensions could harbor forces, particles, or even entire universes that somehow interact with our own in ways we have yet to truly understand or detect. Perhaps the fundamental forces we experience, like gravity, are actually much stronger in these higher dimensions, with only a fraction of their true strength leaking into our 3-dimensional world. This could offer a profound explanation for why gravity is so much weaker than the other fundamental forces. The intricate mechanisms by which these dimensions are hidden or compactified, and even more captivating, how they could potentially be accessed or influenced by our universe, are tantalizing mysteries patiently awaiting theoretical and experimental exploration. Could we, in the distant future, learn to manipulate space-time in a way that allows us to gently unfurl these hidden dimensions, revealing entirely new realities? This concept challenges our very notion of what space truly is, expanding our cosmic imagination to encompass a universe that is far richer, far more multi-layered, and infinitely more mysteriously complex than we currently perceive. The quiet whispers of higher dimensions beckon us to reconsider the very architecture of reality itself. The very concept of time itself may hold mysteries that subtly yet profoundly challenge our current understanding. While we effortlessly perceive time as a linear progression, a relentless forward-moving river carrying us from past to present to future, theoretical advancements gently suggest that new, astonishing aspects of time might be waiting to be unveiled. Is time truly an unchangeable universal constant, or is it more malleable, capable of being subtly bent and twisted under extreme conditions? Our current understanding, anchored by general relativity, already reveals time's inherent malleability when it interacts with gravity and speed. Near a massive black hole, for instance, time slows down dramatically, a phenomenon known as time dilation. This gentle bending of time reminds us that our intuitive everyday experience is just one facet of its true complex nature. But what if there are even deeper mysteries? What if its relationship with space is more intertwined, more fluid than we currently comprehend, especially under conditions far beyond our current experience? Perhaps at the earliest moments of the universe, or within the heart of a black hole, space and time cease to be distinct entities merging into a single fundamental fabric in ways we can only begin to imagine. Moreover, the truly mind-bending possibility of the existence of phenomena that allow for non-linear temporal experiences or connections gently beckons our imagination. Could there be subtle wormholes through time or quantum effects that link moments in the past and future in ways that defy our linear perception? These are not mere science fiction dreams. They are profound theoretical inquiries that push the boundaries of what time truly is. The ultimate fate of the universe also poses a mystery intrinsically intertwined with the fabric of space-time. While theories such as the cold, empty heat death, the crushing Big Crunch, or the violent Big Rip provide speculative endpoints based on our current understanding of dark energy and cosmic expansion, the actual mechanisms and outcomes could be far, far different. These ultimate fates could be profoundly influenced by unforeseen aspects of space-time and entirely new physical laws that are yet to be theorized or discovered. The gentle, relentless flow of time, in its deepest sense, remains one of the universe's most enduring and captivating enigmas, inviting us to forever ponder its true nature as we extend our gaze to the parts of the cosmos that lie beyond our observable limits. The universe could be teeming with cosmic structures, so vast, so complex, or so fundamentally different from anything we've observed that they gently challenge our very conceptions of matter-space and the laws of physics. Imagine a sculptor working on an infinite canvas, creating forms beyond our wildest dreams. Our known universe, with its swirling spiral galaxies, its serene ellipticals, its delicate lenticulars, and its whimsical irregulars, already presents a vast and beautiful catalog of galactic structures. Yet the profound potential for undiscovered types of galaxies that could exist in the universe's most distant or hidden regions is a topic ripe for quiet speculation and wonder. These hypothetical structures, existing beyond the observable universe's familiar 93 billion light-year diameter, represent the true frontiers of cosmic speculation and relentless scientific inquiry. They are like whispers from a hidden dimension, hinting at possibilities we've barely begun to dream of. One captivating possibility that gently beckons our imagination is the existence of superclusters or hyperclusters. While our observable universe proudly displays magnificent superclusters, those massive groupings of galaxies and galaxy clusters like immense cosmic cities, it's conceivable that beyond our sight, there exists an even more immense, a more intricate layer of cosmic organization. Imagine these hyperclusters as cosmic continents dwarfing even the largest known formations. These colossal entities might gracefully span hundreds of billions of light years, containing not just individual galaxies and galaxy clusters, but entire intricate webs of superclusters, all intricately linked in a vast unseen cosmic lattice of dark matter and energy. Their sheer scale would fundamentally challenge our current understanding of how cosmic structures can grow and organize themselves. The formation and evolution of such hyperclusters would be a profound testament to the power of gravity and the pervasive influence of dark matter and dark energy, shaping the universe's large-scale structure in ways we can barely imagine. They could be the true dominant features of the universe, with our observed superclusters being merely tiny local towns within these grand cosmic metropolises. The gravitational dynamics within these hyperclusters would be immensely complex, influencing the motion and evolution of galaxies over unimaginable scales. Their very existence would push the boundaries of our cosmological models, forcing us to consider a hierarchical structure of the universe that is far grander and more layered than we currently comprehend. It's a thought that humbles us, reminding us that even the grandest structures we observe might be but fragments of something far, far larger, silently orchestrating the cosmic dance from beyond our view. Another profoundly speculative idea that quietly resonates in the minds of cosmologists is that of dark galaxies or dark matter conglomerates. Imagine galaxies not as shimmering islands of light, but as vast invisible entities composed almost entirely of dark matter, with very few, if any, ordinary stars. These ghostly galaxies would be nearly invisible to our current detection methods, which rely heavily on the light emitted by stars, gas, and dust. It's like trying to find a shadow in a dark room. You know it's there because of what it affects, but you can't truly see it. We might infer their presence only through their subtle yet significant gravitational pull on surrounding visible matter, or perhaps by their influence on the cosmic microwave background radiation. The existence of such dark galaxies could provide critical new insights into the fundamental nature of dark matter itself, revealing its distribution, its interaction properties, and its profound role in the structure and dynamics of the cosmos. Could these dark galaxies harbor unique forms of dark chemistry, where hypothetical dark particles interact in ways completely unfamiliar to us? Could they even be home to dark life, entirely new forms of existence, operating under physical principles radically different from those in our own luminous universe? These are deep, thought-provoking questions that push the boundaries of imagination. The existence of such structures would fundamentally alter our understanding of cosmic evolution and the distribution of matter and energy in the universe. It would suggest that the visible cosmos is merely a luminous frosting on a far vaster, darker, and more mysterious cake, silently shaped by unseen forces and teeming with hidden, unimaginable possibilities. Beyond the familiar classifications, there's a quiet whisper of galaxies, with unconventional forms, structures that defy our neat categories and suggest a universe of boundless creativity. These might be galaxies whose shapes are the direct result of unique or extreme conditions, forging them into cosmic anomalies. Imagine galaxies with highly irregular shapes, far more chaotic and unpredictable than our current classification schemes of spirals, ellipticals, or lenticulars allow. Perhaps these are galaxies that have undergone truly unusual evolutionary paths due to their extreme environment, such as intense gravitational interactions with neighboring galaxies, colossal cosmic collisions that leave behind tangled, beautiful wrecks. Or perhaps they exist in regions exposed to extreme radiation from a superactive quasar, or cascade of gamma-ray bursts influencing star formation and galactic structure in ways we've yet to comprehend. Think of a cosmic artist, not bound by conventional forms, sculpting nebulae into breathtaking, never-before-seen patterns. These are not merely variations on a theme. They represent a fundamental departure from the expected, challenging our understanding of galactic formation and evolution. Their discovery would force us to expand our models to reconsider the intricate interplay of forces that shapes these cosmic islands. Such galaxies would be profound testaments to the universe's boundless capacity for unexpected beauty and complexity, reminding us that even in the seemingly familiar realm of galactic forms, there remain countless wondrous surprises waiting to be gently unveiled. Then there are the primordial galaxies, whispers from the universe's earliest dawn, significantly different in composition and structure from those that formed much later. Imagine the cosmos in its tender infancy, a time before the universe was enriched with the heavy elements forged in the hearts of stars. These primordial galaxies, likely much smaller, less organized, and more diffuse than their modern counterparts, would contain stars made almost entirely from hydrogen and helium, the universe's first, most fundamental elements. These are the first generations of stars, blazing with an intensity and composition unlike anything we see today. They were the trailblazers, the pioneers that began the cosmic cycle of star formation and element creation. Their detection would provide invaluable information about the universe's initial conditions, offering a direct glimpse into the very first moments of cosmic structure formation. How did these nascent galaxies coalesce from the primordial gas? What were the conditions that prevailed shortly after the Big Bang that allowed for their birth? Studying them would be like examining the very first brushstrokes on the cosmic canvas, revealing the artist's initial intentions. The light from these earliest galaxies would be incredibly redshifted, stretched by billions of years of cosmic expansion, making them extraordinarily faint and challenging to observe. Yet new generations of telescopes designed to capture these ancient whispers are on the horizon. Their discovery would not only confirm our models of early universe evolution, but also open a profound new chapter in our understanding of how the universe transformed from a homogeneous soup of particles into the complex galaxy-filled cosmos we inhabit today. These ancient faint lights are silent storytellers waiting to share the tale of cosmic genesis. Finally, the captivating possibility of mirror galaxies, a truly mind-bending concept stemming from the speculative theory of a parallel universe or a mirror world, gently opens up fascinating avenues for exploration. Imagine for a moment that for every known particle and force in our universe, there exists a corresponding mirror particle and mirror force in a parallel reality, a realm subtly separated from our own. While entirely hypothetical and deeply embedded in theoretical speculation, these mirror galaxies would be composed of mirror matter, a kind of matter that interacts with our known universe in fundamentally different, almost imperceptible ways. Perhaps mirror matter interacts with our ordinary matter only through gravity or through some incredibly weak, as yet undiscovered, mirror force. This means we wouldn't see them directly with our telescopes, as their mirror light would not interact with our eyes or detectors. However, their presence might be subtly observable through indirect gravitational effects, perhaps by the gravitational lensing of light around an unseen mass, or by unusual patterns in the movement of visible galaxies that can't be explained by our ordinary matter, or even dark matter. They might also leave faint, telltale signatures in the cosmic microwave background if our universe subtly bumped into a mirror universe in its infancy. This profound concept challenges the very notion of what constitutes reality, suggesting that our universe might be just one side of a cosmic coin. The possibility of mirror galaxies invites us to consider a cosmos far more intricate and dualistic than we currently perceive, offering a tantalizing, almost poetic glimpse into realms where physics operates under subtly different mirrored rules, awaiting our gentle, imaginative exploration. At the very edge of the observable universe, where the familiar light begins to fade, and the known gives way to the unknown, phenomena occur that gently stretch the limits of our understanding, profoundly challenging our perceptions of cosmology, physics, and the very nature of reality itself. This elusive boundary, gracefully known as the cosmic horizon, is not a physical edge in space like the end of a vast plain. Instead, it is a subtle yet absolute limit imposed by the finite speed of light and the immense age of the universe. Light from beyond this horizon, originating from sources even further away, simply has not had enough time to reach us since the Big Bang. It's like standing on a ship in the middle of a vast ocean. The horizon isn't a wall, but simply the limit of what you can see. These distant regions, therefore, remain elegantly beyond our current observational capabilities, forever hidden by the veil of cosmic time and the unyielding speed of light. However, the gentle whispers of theoretical physics and cosmology still provide us with profound insights into what might quietly occur at this profound frontier of visibility. One profound phenomenon that defines this edge of the observable universe is the redshifting of light to an extreme degree, a majestic effect known as cosmological redshift. Imagine light not as a steady beam, but as a series of gentle waves like ripples on a pond. As the universe relentlessly expands, the very fabric of space between us and a distant light source stretches, causing these light waves to stretch along with it. When light waves stretch, their wavelength increases, subtly shifting their color towards the red end of the electromagnetic spectrum, much like a musical note dropping in pitch as its source moves away. At the cosmic horizon, this effect is maximized due to the immense unimaginable distances involved and the accumulated stretching of space over billions of years. The light from objects at this extreme edge is so incredibly redshifted that it becomes nearly, if not entirely, undetectable with current technology. It's like trying to hear a whisper from across a vast canyon. The sound is stretched and diluted until it becomes inaudible. This extreme stretching of light also carries a profound temporal message. It means that the objects we can theoretically perceive near this edge appear much older and less evolved than those closer to us. We are essentially looking back in time, catching a glimpse into the universe's true infancy. The light from these nascent galaxies and primordial structures, having journeyed for nearly the entire age of the universe, reveals them as they were billions of years ago before they fully matured. This provides us with an invaluable, almost poetic glimpse into the universe's infancy, a direct window into its earliest, most formative moments. Studying these extremely redshifted objects allows cosmologists to test their models of early galaxy formation and the conditions of the primordial cosmos. This cosmic redshift, therefore, is not merely a technical detail. It is a fundamental property of our expanding universe, acting as both a veil that hides and a window that reveals the deepest, most ancient secrets of our cosmic past. Another truly intriguing phenomenon at the edge of the observable universe is the potential visibility of the cosmic microwave background, CMB radiation, as it would have appeared from those incredibly distant regions. Imagine the CMB, that ancient afterglow of the Big Bang, as a vast ethereal fog that filled the early universe. This CMB is a precious snapshot of the universe when it was barely an infant, just about 380,000 years old, a time long before the first stars flickered into existence, or the first galaxies began to coalesce. It's the moment the universe cooled enough for light to travel freely, bathing everything in its soft, uniform glow. From our vantage point on Earth, we see this CMB coming from all directions, a remarkably uniform warmth across the entire sky. But if we could conceptually travel to the very edge of our observable universe, to that far-off horizon, what would we see? From that incredibly distant perspective, the CMB would still be present surrounding us. Observing the CMB from the very edge of the observable universe, or understanding how it would look if we could offer unique insights into the early universe's properties and the precise distribution of matter and energy during those crucial moments immediately after the Big Bang. It would be like looking at a photograph of a baby and understanding the conditions in the room where that photo was taken, even if that room is now billions of light years away. The subtle variations in the CMB, which are the seeds of all cosmic structure, would be seen differently from that edge, potentially revealing new information about the universe's overall geometry and its initial conditions, gently pushing the boundaries of what we can infer about the earliest tapestry of existence. Additionally, theoretical models quietly predict the existence of structures and objects just beyond our observational reach that could subtly yet profoundly influence the formation and evolution of the cosmic web within the observable universe. Imagine a grand unseen gravitational magnet just out of sight, gently tugging at the luminous threads of galaxies we can see. These unseen structures could include even more massive clusters of galaxies than we've yet detected, or even larger superclusters extending far beyond our current telescopic view. They might also encompass immense, truly large voids, vast empty regions of space where galaxies are incredibly sparse. The powerful gravitational effects of these unseen giants, or these colossal absences of matter, might be detectable as subtle influences on the motion and distribution of galaxies near the observable universe's edge. For example, our own Milky Way galaxy, and indeed our entire local group of galaxies, appears to be streaming towards a mysterious massive concentration of matter known as the Great Attractor, which lies partially obscured from our direct view. While we understand much about the Great Attractor within our observable limits, the existence of even larger unseen gravitational pulls from beyond the horizon could explain some of the more puzzling, large-scale flows of galaxies. These unseen influences, these cosmic architects operating just beyond our visual field, highlight the interconnectedness of the cosmos. They suggest that the grand tapestry of the universe is far larger than what we can currently perceive, with unseen threads subtly shaping the visible patterns, reminding us that the story of cosmic evolution extends far beyond the familiar pages we've already read. The quantum fluctuations that occurred at the very moment of cosmic inflation might also leave incredibly subtle yet profound imprints on the very edge of the observable universe. Imagine the universe in its most primordial state, not as a calm, empty void, but as a bubbling, effervescent quantum foam, constantly teeming with tiny fleeting bursts of energy and matter popping in and out of existence. These quantum fluctuations, though infinitesimally small in their origin, were dramatically magnified by inflation, stretching to cosmic scales in an instant. These amplified fluctuations are believed to be the fundamental seeds for all cosmic structure, the initial density variations that eventually grew through gravity into the galaxy's clusters and the vast cosmic web we see today. Studying the edge of the observable universe, particularly through the detailed analysis of the cosmic microwave background CMB, which carries these ancient imprints, could therefore provide crucial clues to understanding inflationary theory itself. Are there specific patterns in the CMB that are consistent only with certain inflationary models? Do we see evidence of particular kinds of quantum fields at play in those earliest moments? More profoundly, it could offer insights into the quantum origins of the cosmos itself. It's like finding a single incredibly faint fingerprint on an ancient artifact. That fingerprint might reveal the true identity of the creator. The subtle temperature variations and polarization patterns in the CMB are direct echoes of these primordial fluctuations, carrying information from a time before any stars or galaxies existed. By meticulously analyzing these faint whispers from the cosmic dawn, we hope to unlock the deepest secrets of the universe's birth and the fundamental quantum processes that gently laid the foundation for everything that followed, even in the realms forever hidden from our direct sight. Finally, the profound concept of horizon problem resolution is a phenomenon intimately tied to the remarkable uniform temperature of the CMB across the sky. Imagine the early universe as a vast, rapidly expanding sea. The horizon problem asks, how is it that regions of the CMB that are incredibly far apart from each other so far? In fact, that light could not have possibly traveled between them. Since the Big Bang, meaning they couldn't have communicated or exchanged heat, still have almost exactly the same temperature. It's like finding two distant islands in an ocean that have the exact same temperature, even though they've never been connected by currents. Without communication, how did they equilibrate? The observable universe's edge might hold crucial clues to this uniformity, because it is at this very boundary that we are looking back to the earliest moments when these seemingly causally disconnected regions existed. The leading explanation for this puzzling uniformity is the theory of cosmic inflation. This theory suggests that in the universe's earliest moments, it underwent an unimaginably rapid faster-than-light expansion rates, a phenomenon that doesn't violate Einstein's theory of relativity because it's the space between objects expanding, not objects moving through space faster than light. This period of explosive superluminal expansion could have allowed regions that are now incredibly distant from each other to have once been in very close causal contact, to have communicated and equilibrated their temperatures before inflation stretched them apart to vast uncommunicable distances. This rapid expansion then essentially smoothed out any initial temperature irregularities, explaining the CMB's remarkable smoothness across vast distances. So when we study the uniform glow of the CMB, particularly at the edges of our observable universe, we are indirectly witnessing the profound power of inflation. The solution to the horizon problem, rooted in this incredible inflationary epoch, therefore tells us something fundamental, not just about our observable cosmos, but about the very earliest, most profound dynamics that shaped the entire sprawling universe, including the vast regions that remain perpetually beyond our direct gaze. It's a testament to how a problem of uniformity can hint at the most dramatic and rapid events of creation. The quest to understand the universe often brings us to the shimmering threshold of the observable and into the realm of gentle speculation about what lies beyond. Among the most intriguing prospects is the potential detection of unknown signals originating from beyond the observable universe. These signals, inherently mysterious due to their origin from regions we simply cannot see, could potentially carry profound information about the early universe, the very nature of cosmic expansion, and even the tantalizing existence of other universes or dimensions. Imagine listening to a vast, silent cosmic symphony, and suddenly from beyond the reach of our ears, you catch a faint, unfamiliar note, a melody from an unseen choir. Such a whisper from the cosmic deep would revolutionize our understanding, pushing the boundaries of what we thought was knowable. One fascinating category of these unknown signals could be gravitational waves. Unlike electromagnetic radiation, which includes the light, we see radio waves and X-rays. Gravitational waves are ripples in the very fabric of space-time itself. Imagine space-time as a vast, supple sheet, and when massive cosmic events occur, like the violent collision of two black holes, they send out these distortions, these ripples across the sheet. The beauty of gravitational waves is that they travel through the cosmos largely unimpeded by matter. They don't get absorbed by dust clouds or blocked by galaxies. This means they offer an incredibly pristine glimpse into the universe's most cataclysmic events, even if those events occurred billions of years ago in regions now far beyond our visible horizon. If we were able to detect gravitational waves from beyond the observable universe, they could inform us about events of unimaginable scale and violence that occurred in the early universe. Perhaps the chaotic ancient mergers of supermassive black holes from a time before our galaxies even formed, or incredibly powerful phase transitions in the vacuum state of the universe. Moments when the fundamental properties of space itself subtly changed. They might even carry the telltale signatures of cosmic strings, those hypothetical, incredibly thin defects in space-time remnants from the Big Bang that could stretch across the entire cosmos. Such a detection would be like listening to the echoes of creation itself, offering a direct, unfiltered narrative from the earliest, most extreme moments of universal history, unmarred by the intervening dust and stars. It's a profound thought that the deepest secrets of the cosmos might be whispered to us not through light, but through the very vibrations of space and time. Another potential source of these elusive, unknown signals might come from neutrinos. These are truly remarkable subatomic particles, often called ghost particles. Because of their incredibly peculiar nature, they have an almost negligible mass, so tiny it was once thought they had none at all, and they interact incredibly weakly with matter. Imagine tiny silent messengers, almost ethereal, capable of traversing vast cosmic distances without ever bumping into anything. Because of this incredibly weak interaction, neutrinos can escape from the densest regions of space, like the cores of exploding stars or the fiery hearts of active galaxies, and travel unimpeded across the universe, carrying information that light simply cannot. Detecting ultra-high energy neutrinos from beyond the observable universe would be a monumental achievement, offering crucial clues about the conditions of the early cosmos. Such energetic neutrinos could be produced in the most extreme astrophysical environments, far beyond our current view. Their detection could reveal ancient processes related to the formation of the first structures, perhaps even hint at physics that deviate from the standard model, our current best understanding of fundamental particles and forces. Imagine receiving a message from a realm where the rules of physics are slightly different, carried by these tireless, almost undetectable couriers. These neutrinos would be like silent time capsules, preserving information from an epoch too ancient and too distant for light to illuminate. The challenge lies in their elusive nature. Detecting them requires massive, incredibly sensitive detectors, often buried deep underground or submerged in ice, patiently waiting for the rare fleeting interaction that reveals their presence. But the potential rewards, the secrets they might whisper from the unseen cosmos, make the endeavor truly worthwhile. Those amplified quantum fluctuations, magnified so dramatically during the period of cosmic inflation, might also leave subtle yet detectable imprints as faint anomalies in the cosmic microwave background, CMB radiation. Remember the CMB as the soft ancient afterglow of the Big Bang, a nearly uniform warmth across the sky. But beneath this uniformity lie incredibly tiny variations in temperature and polarization, like the delicate wrinkles on an ancient piece of parchment. These imprints could manifest as specific patterns or cold spots within the CMB that are not easily explained by our standard cosmological models. It's like finding a mysterious, unexplainable pattern in a pristine snowfield, hinting that something unusual occurred there. These inexplicable patterns or cold spots could subtly hint at the influence of structures or phenomena beyond our observable horizon. Perhaps they are the faint gravitational echoes of a supervoid or a massive cluster of dark matter that lies just outside our visible bubble. Even more tantalizingly, such anomalies could be signatures from other universes in a multiverse scenario. Imagine if our universe, this cosmic bubble, had once gently collided or subtly interacted with another bubble universe during its incredibly early inflationary phase. That interaction, even if brief and gentle, might have left a distinct, measurable imprint on the CMB that our instruments could one day detect. These faint, subtle variations therefore represent a potential pathway to truly revolutionize our understanding of cosmic origins and the very architecture of reality. They are like cryptic messages from across the cosmic abyss, waiting for our collective ingenuity to decipher their profound meaning and reveal the hidden dimensions of existence. Additionally, theoretical constructs like dark matter axions could potentially generate detectable signals if these hypothetical particles truly exist and interact with our observable universe from beyond its perceived boundaries. Remember, axions are proposed as incredibly light, weakly interacting particles that could make up a significant portion of the universe's mysterious dark matter. While they are notoriously difficult to detect directly due to their elusive nature, it's theorized that under specific incredibly rare conditions or in the presence of strong magnetic fields, axions might convert into photons, particles of light. This conversion could produce unique, faint electromagnetic signatures in certain energy ranges that our sensitive instruments might one day be able to pick up. Imagine a vast unseen ocean of dark matter axions permeating the cosmos, including the regions beyond our observable reach. If, for instance, a particularly dense clump of these axions were to encounter a strong magnetic field in an unobservable distant galaxy, they might, in theory, generate a weak but distinct stream of X-rays or radio waves. Discovering such signals would be a monumental breakthrough, not only definitively proving the existence of axions, solving one of the biggest puzzles in physics, but also offering an incredible window into the larger unseen cosmos. It would provide indirect evidence of the composition and dynamics of dark matter in regions we cannot directly observe, giving us a clearer picture of the universe's total inventory and how it behaves. These faint hypothetical whispers from the realm of dark matter are a testament to the persistent scientific quest to unveil the unseen architects of our universe, patiently listening for their subtle cosmic song. Black holes, those incredibly enigmatic entities we know of, serve as profound cosmic laboratories for testing the very limits of physics. Imagine them as cosmic drainpipes where the known laws begin to warp and break down. Those that are theorized to be lying beyond the observable universe in regions we cannot yet see or study directly. Tantalize scientists with the immense potential to hold the deepest secrets about the universe's most profound mysteries. These unseen behemoths represent the ultimate frontiers of knowledge where gravity reigns supreme and our understanding is truly put to the test. One such secret pertains to the very nature of quantum gravity. Black holes present an immense challenge to our understanding by bringing the fundamental principles of general relativity, which exquisitely describes gravity at macroscopic scales, the bending of space-time into direct conflict with quantum mechanics, which meticulously describes the microscopic world of particles. At the incredibly dense core of a black hole, these two foundational theories simply do not agree, indicating a profound incompleteness in our understanding of reality. Black holes beyond our observable universe might exhibit behaviors or properties that provide crucial insights into this elusive unification problem. For example, the way in which these distant ancient black holes might slowly evaporate through Hawking radiation, a theoretical process where black holes slowly lose mass over time, could offer crucial clues about how gravity operates at the quantum scales. If we could detect or infer patterns in this radiation from extremely ancient black holes, it could potentially lead to a complete theory of quantum gravity, a unified framework that seamlessly integrates these two powerful descriptions of reality. It's like finding a Rosetta Stone for the universe, where the language of gravity and the language of the quantum world finally become one. Another profound secret involves the very formation and evolution of the early universe. Imagine the cosmos just moments after the Big Bang, a maelstrom of energy and rapidly expanding space-time. Primordial black holes, those hypothetical black holes theorized to have formed incredibly soon after the Big Bang through the collapse of tiny density fluctuations, could exist in immense abundance beyond the observable universe. Unlike stellar black holes, these would have formed directly from the primordial soup, not from dying stars. These incredibly ancient compact objects, if they exist, could inform us profoundly about the conditions of the early universe, including the precise distribution of matter and the true nature of dark matter. If primordial black holes contribute significantly to dark matter itself, meaning that a large portion of the universe's unseen mass is actually comprised of these ancient invisible black holes, then detecting their subtle signatures, such as the gravitational waves emitted from their ancient collisions and mergers, could unveil the true composition and behavior of the universe's dark sector. Imagine two such primordial black holes, perhaps tiny, colliding billions of years ago in a region far beyond our sight. The ripples they create in space-time would travel unimpeded, eventually reaching our detectors, telling us about the universe's earliest, most extreme moments. This profound connection between primordial black holes and dark matter offers a compelling pathway to unraveling two of the universe's most enduring enigmas. Patiently waiting for the subtle echoes of their ancient dance to reach us across cosmic time. The information paradox, a deep and perplexing puzzle concerning the ultimate fate of information that falls into a black hole, also hides profound secrets about the fundamental principles of the universe. Imagine a book falling into a black hole. Does the information contained within that book, every word, every idea, truly disappear, forever erased from existence? This question lies at the heart of the paradox. General relativity suggests that information is destroyed at the black hole's singularity, simply vanishing. However, quantum mechanics, another foundational theory, posits that information can never truly be destroyed. It must always be preserved, merely transformed. This creates a profound contradiction at the very core of our understanding of physics. Do black holes beyond the observable universe somehow destroy information, as classical theories suggest, defying the tenets of quantum mechanics? Or is information somehow preserved, perhaps encoded in the subtle properties of Hawking radiation, or transferred to another universe as required by quantum mechanics? The resolution of this paradox would be a monumental breakthrough, one that could fundamentally revolutionize our understanding of information entropy, the measure of disorder, and the very fabric of space-time itself. It would force us to reconcile these two great pillars of physics, or perhaps even to discover entirely new physics that resolves the contradiction. The information paradox is a cosmic riddle, one that black holes, particularly those ancient unseen ones, might hold the key to solving patiently, waiting for our minds to grasp their deepest, most confounding secret. Supermassive black holes beyond the observable universe could also reveal profound insights into the intricate processes of galaxy formation and evolution, particularly on scales and in environments far different from those we can currently observe. In our observable universe, we've learned that these colossal black holes residing at the centers of most large galaxies play a crucial role in shaping their host galaxies, influencing star formation and the distribution of gas. But what if these interactions are profoundly different in regions of the universe that are far older, or have different densities of matter, or are subjected to different gravitational influences from cosmic structures just out of our sight? The intricate interaction between these supermassive black holes and their surrounding dark matter halos, the vast invisible envelopes of dark matter that hold galaxies together, along with the interstellar gas and the countless star systems, could provide truly unique insights into the dynamics of galaxy formation in different cosmic epochs and environments. Perhaps in some unobservable regions, supermassive black holes grew much faster or much slower, leading to vastly different galactic structures. Or perhaps the relationship between the black hole's growth and the formation of stars in its host galaxy is not universal, but varies with cosmic conditions. The study of these unseen titans, even through indirect means, could unlock new chapters in the story of how galaxies, the fundamental building blocks of the visible universe, came to be, and how they continue to evolve across the vast unseen tapestry of the cosmos. The existence of black holes with properties or behaviors not predicted by current theories could gently open the door to entirely new physics. While black holes are well-established objects in cosmology, perfectly described by Einstein's general relativity, the possibility remains that in the universe's extreme corners or under conditions we can't yet imagine, they might exhibit characteristics that defy our current understanding. This could include black holes in higher dimensional space, as softly predicted by some theoretical models, like string theory. If those extra dimensions exist, perhaps black holes can extend into them, leading to unique gravitational signatures or properties that we wouldn't expect in our four-dimensional spacetime. Or perhaps there are black holes with unusual charge or spin characteristics that challenge our understanding of astrophysical processes and the limits of matter under extreme gravity. Could there be naked singularities, regions where the singularity at a black hole's core is not hidden by an event horizon? Defying cosmic censorship, these anomalies, if they could ever be detected or inferred, would hint at the existence of exotic particles, fields or fundamental principles of physics that only manifest under the incredibly extreme conditions present at black hole event horizons. They are like cosmic anomalies urging us to rethink our foundational assumptions. Such discoveries would not just refine our current models. They would fundamentally reshape our entire conceptual framework, offering a profound glimpse into the hidden depths of reality and the boundless complexity of the universe itself. The whispers from these strange black holes beckon us toward a physics yet to be written. Wormholes, a concept that has quietly fascinated scientists and science fiction enthusiasts alike for decades, are hypothetical passages through space-time that could in theory create shortcuts between incredibly distant parts of the universe, or even provide gateways to entirely other universes. Imagine folding a piece of paper in half and then poking a hole through it with a pencil. The pencil creates a shortcut between 2 points that were originally far apart on the flat surface. That's the simplest analogy for a wormhole. According to general relativity, the very theory that beautifully describes the gravitational interaction of matter and energy wormholes are possible configurations of space-time. They can theoretically connect 2 separate points in space and time, much like a tunnel, with 2 ends in different locations, or even different cosmic eras. The intriguing possibility that wormholes could connect us to distant parts of the universe opens up visions of interstellar travel that gracefully bypass the immense vast distances of empty space. This would allow for almost instantaneous or near instantaneous movement across galaxies, transforming all our understanding of cosmic journeys. Imagine being able to hop from the Milky Way to Andromeda in mere moments rather than millions of years. This would not only revolutionize our technological capabilities for travel and communication across the cosmos, but also fundamentally alter our perception of distance and separation, making the universe feel much smaller and more accessible. Furthermore, if wormholes could indeed connect to other universes, as some subtle interpretations of quantum mechanics and string theory gently suggest, they would offer a tangible, almost dreamlike method of exploring the multiverse. Imagine being able to step from our cosmic bubble into another entirely different one, where the laws of physics are subtly altered, or where galaxies take on bizarre, unfamiliar forms. Through these extraordinary connections, we might gain profound insights into the fundamental nature of reality. Exploring firsthand the diverse physical laws and unique cosmic landscapes that define these alternate universes. It's a tantalizing prospect, offering a pathway to not just observe, but to actually experience the boundless diversity of existence beyond our current reach, making the universe an even grander, more interconnected tapestry than we ever dared to imagine. However numerous formidable challenges and profound mysteries surround the practical use and even the very existence of wormholes, imagine trying to hold open that folded piece of paper with a pencil. The paper naturally wants to spring back to its original flat state. Similarly, theoretical models gently suggest that keeping a wormhole open would require a very specific exotic form of matter with negative energy density. This is not the ordinary matter we know, which has positive energy density. Exotic matter, as its name suggests, is something that has not yet been found in the observable universe, and its properties are purely theoretical. This hypothetical matter would essentially counteract the immense gravitational pull that would naturally cause a wormhole to collapse almost instantaneously, stabilizing the tunnel just long enough for something or someone to pass through. The creation and, indeed, the maintenance of a wormhole therefore hinge on the existence of these incredibly rare, almost mythical materials and energy types that are speculative at best with our current understanding of physics. It's like trying to build a bridge without knowing if the materials for its construction even exist. Even if wormholes were naturally occurring, navigating or even locating a wormhole, should they exist, poses significant technical challenges. Detecting the incredibly subtle gravitational distortions that would signify the entrance to a wormhole would likely involve observing the unique gravitational effects it exerts on surrounding matter, and light a task requiring unbelievably sensitive instruments and potentially entirely new methods of astronomical observation far beyond our current capabilities. It's a gentle reminder that even the most elegant theories face immense practical hurdles when brought to the cosmic stage. Beyond the challenges of exotic matter, the very notion of traveling through a black hole to emerge in another part of the cosmos or a different dimension confronts us with the profound and perplexing problem of singularity at a black hole's core. According to our current understanding from general relativity, at a black hole's heart lies a singularity, a point of infinite density and zero volume where the laws of physics as we know them simply cease to apply. It's a place where our equations break down a cosmic wall beyond which our current understanding cannot penetrate. This is not just a theoretical oddity. It's a fundamental barrier to any form of physical travel through a black hole. How could matter, or even more profoundly, information pass through this singularity intact? How could a spacecraft, or even the subtle quantum information of a single particle, survive a journey through a point of infinite gravitational force and emerge coherently on the other side? This is a profound mystery, one that challenges our most deeply held understanding of physics. While some speculative theories, like certain interpretations of string theory, propose ways in which the singularity might be resolved, perhaps replaced by a fuzzball of strings, or connected to other dimensions, these remain highly theoretical. The journey through a black hole to a wormhole, as depicted in many tales, remains a beautiful, yet incredibly daunting theoretical dream. It forces us to confront the very limits of our knowledge, reminding us that the universe holds secrets so profound, they may forever remain beyond our grasp, inviting us to simply wonder at the sheer power and mystery of these cosmic behemoths. The early universe, that incredibly brief and profoundly influential period, just after the Big Bang, holds crucial whispering clues about the vast cosmos that extends far beyond our current observable limits. Imagine the universe not as the sprawling galaxy-filled expanse we see today, but as an unimaginably tiny, dense, and searingly hot entity brimming with pure potential. This primordial epoch perfectly encapsulated in the faint omnipresent glow of the cosmic microwave background. CMB radiation provides us with a precious snapshot of the universe when it was barely an infant, only about 380,000 years old. By meticulously studying, the CMB scientists gain profound insights into the extreme conditions that prevailed in that nascent universe, gently offering tantalizing hints about the boundless cosmos that lies forever beyond our current observational capabilities. It's like finding a single perfectly preserved ancient scroll that tells the story of creation from its very first word. One of the key, most compelling clues gleaned from the early universe is the remarkable uniformity of the CMB across the sky. Imagine the sky as a vast canvas, and everywhere you look, the temperature of this ancient light is almost exactly the same, with only incredibly tiny subtle variations. This surprising uniformity presents a profound puzzle. How is it that different regions of the universe, even those that are not causally connected, meaning light, has not had enough time to travel between them since the Big Bang, so they couldn't have influenced each other, still possess such similar temperatures? It's like finding two perfectly identical untouched puddles, separated by an immense desert, implying some prior unifying event. This observation has gracefully led to the development of the inflation theory, a brilliant and elegant idea which posits that the universe underwent an unimaginably rapid exponential expansion shortly after its birth. Imagine that tiny primordial universe inflating to an astronomical size in less than a blink of an eye. This sudden superluminal stretching of space essentially smoothed out any initial irregularities in temperature or density. The profound implication of inflation is that the regions beyond our observable universe were once intimately connected to our own. Before inflation stretched them apart to distances that light could no longer bridge, they were part of the same tiny uniform cosmic bubble. Therefore, they might subtly share some of its fundamental properties, suggesting a cosmos that is homogeneous on the largest scales, extending far beyond what we can see. This connection hints at a vast underlying unity to the universe, a continuous tapestry woven from the same fundamental threads even in the realms forever hidden from our sight. The quantum fluctuations that gently occurred during inflation are another incredibly crucial clue, acting as the universe's most ancient architects. Imagine the universe in its earliest, most primordial state, not as a perfectly smooth and empty void, but as a vibrant, effervescent sea of pure quantum potential. In this incredibly tiny, unimaginably brief moment before inflation took hold, the universe was teeming with these fleeting, almost imperceptible quantum fluctuations. These are not random disturbances in the ordinary sense. Rather, they are the inherent restless jiggle of energy and matter at the most fundamental quantum level, constantly appearing and disappearing, even in what seems to be empty space. They are like the subtle shimmering ripples on a microscopic pond inherent to its very nature. The profound magic of inflation is that during this rapid exponential stretching of space, these minuscule, almost invisible quantum fluctuations were dramatically amplified and stretched to cosmic scales. Imagine those tiny pond ripples suddenly expanding across an entire ocean. What was once a quantum whisper became a cosmic roar. These amplified fluctuations, these delicate seeds of variation in the early universe, then became the fundamental starting points for the formation of all the magnificent future structures in the universe, the shimmering galaxies, the colossal clusters of galaxies, and the intricate, vast cosmic web that interweaves the entire universe. Without these initial seeds, without these tiny imperfections, the universe would have remained a smooth, featureless expanse, devoid of any discernible structure. Observing these fluctuations in the CMB cosmic microwave background provides us with an almost direct and valuable link to the processes occurring in the very early universe, suggesting that similar structures could exist throughout the cosmos, even in parts we cannot directly observe. The distribution and nature of these fluctuations hold profound insights, gently informing our models of cosmic inflation and offering crucial clues into the physics governing the universe at its most fundamental level. It's like finding an ancient blueprint that, though faded, still clearly outlines the grand design of an entire city, even the parts that haven't been built yet. The quiet whispers of these quantum fluctuations from the dawn of time continue to guide our understanding of the universe's grand unseen architecture. The early universe's clues about dark matter and dark energy, those two most mysterious components of the cosmos, extend our understanding far beyond the observable. Imagine a grand cosmic dance where these two unseen partners, dark matter and dark energy, subtly choreograph the evolution of the universe, the precise way galaxies and galaxy clusters formed and evolved under the profound influence of dark matter. Subtly observable in the CMB's slight anisotropies, those tiny temperature differences strongly implies that dark matter's presence and its fundamental properties are remarkably consistent throughout the entire cosmos. This means that the invisible scaffolding of dark matter that holds our visible galaxies together is likely present in the same way with the same characteristics in regions billions of light years away that we cannot yet see. It suggests a universality to this mysterious substance, a pervasive, unchanging influence across the entire breadth of existence. Similarly, the accelerated expansion of the universe, a phenomenon universally attributed to dark energy, affects the very fabric of the entire cosmos, not just our observable bubble. This suggests that the dynamic properties of dark energy observed within our cosmic horizon apply universally, pushing galaxies apart with an increasing vigor across all scales, seen and unseen. The consistent behavior of these two enigmatic forces, from the smallest gravitational interactions within galaxies to the largest scale cosmic flows, allows us to extrapolate their influence to the unobservable realms. It implies that the ultimate fate of the universe, whether it continues to expand indefinitely, eventually becoming cold and empty, or whether its expansion might one day slow or reverse, is being shaped by the same fundamental forces everywhere. The early universe, through the imprints it left, whispers profound secrets about the unseen drivers of cosmic evolution, guiding us to understand the grand unified choreography of the cosmos, from its very beginning to its ultimate distant future. The study of primordial elements, those foundational building blocks of the universe, such as helium and lithium, formed during the very first few minutes after the Big Bang in a profound process known as nucleosynthesis, offers additional crucial clues. Imagine the universe as a vast primordial furnace, incredibly hot and dense. In those initial moments, before any stars existed, the conditions were just right for protons and neutrons to fuse together, creating the lightest elements. This process was a cosmic alchemy on an unimaginable scale, dictating the initial chemical composition of the entire universe. The relative abundances of these elements, the precise proportions of hydrogen, helium, and trace amounts of lithium and beryllium are remarkably consistent with the predictions of the Big Bang model across all observable regions of the cosmos. This consistency is not a mere coincidence. It is a powerful piece of evidence. It profoundly supports the idea of a uniform set of physical laws and conditions extending throughout the entire universe, including those vast unseen regions beyond our observable limits. If the laws of physics or the initial conditions were significantly different in an unobservable part of the cosmos, the abundances of these primordial elements would likely vary, creating a detectable discrepancy. The fact that we see the same cosmic recipe for these elements everywhere suggests a fundamental homogeneity across the vastness of space. It's like finding the same unique chemical signature in samples taken from every corner of a boundless ocean, implying a common origin and consistent underlying processes. The primordial elements therefore act as silent ancient witnesses, testifying to the universal nature of the Big Bang and the consistent tapestry of physical laws that govern the entirety of existence, both seen and unseen. Lastly, gravitational waves, those incredibly subtle ripples in the very fabric of space-time, generated by truly violent cosmic events, or even the initial tumultuous moments of the universe itself, carry profound information about the very early universe that could extend into the unobservable cosmos. Imagine the universe as a colossal vibrating drum, and these gravitational waves are the sounds of its most ancient and powerful beats. Unlike light, which can be absorbed or scattered by matter, gravitational waves travel largely unimpeded through the cosmos, carrying an untouched, pristine record of their origin. This unique property makes them incredibly powerful probes, capable of piercing through the cosmic fog that existed in the very early universe, a time when light was still trapped. Detecting these incredibly faint waves from the infant universe could unveil phenomena or structures in the cosmic landscape far beyond our current reach. For instance, the theory of cosmic inflation predicts a background of primordial gravitational waves generated by the immense stretching of space in the very first fraction of a second after the Big Bang. If we could detect these primordial waves, perhaps through incredibly subtle patterns in the polarization of the cosmic microwave background, it would provide direct evidence of inflation and offer an unprecedented window into physics at energy scales far beyond what we can achieve in any earthbound laboratory. These waves would be carrying information from a time when the entire universe was contained within a space smaller than an atom, a time when the very fabric of reality was being sculpted. The potential to directly hear the echoes of creation, the faint murmurs of the universe's earliest moments through these elusive gravitational waves, represents one of the most exciting frontiers in modern cosmology, promising to reveal secrets from the deepest, most inaccessible corners of the unobservable cosmos. The known universe, with its myriad forms from spiral to elliptical lenticular to irregular, already presents a vast and beautiful catalog of galactic structures. Imagine peering through a cosmic kaleidoscope, endlessly revealing new intricate designs. Yet the profound potential for undiscovered types of galaxies, that could exist in the universe's most distant or hidden regions is a topic ripe for quiet speculation and wonder. It's like having explored only a few islands in an boundless ocean, knowing that countless other stranger lands might await discovery. These hypothetical structures existing beyond the observable universe's familiar 93 billion light-year diameter represent the true frontiers of cosmic speculation and relentless scientific inquiry. They are like whispers from an unseen realm, hinting at possibilities that stretch the very fabric of our cosmic imagination, reminding us how little we truly know of the full breadth of creation. One captivating possibility that gently beckons our imagination is the existence of ultramassive galaxies structures, far exceeding the sheer size and mass of any galaxies observed thus far. Imagine these as cosmic behemoths, true giants among giants. These hypothetical entities would dwarf even the most massive galaxies we know within our observable universe, containing not just hundreds of billions, but literally trillions of stars, a staggering number that almost defies comprehension. They would span hundreds of thousands of light years across colossal islands of light and gravity in the cosmic night. Their sheer scale would fundamentally challenge our current understanding of cosmic structure formation and the ultimate limits of galaxy formation. How could such immense structures coalesce and maintain their integrity against the relentless pull of expansion? The formation and evolution of such ultramassive galaxies would require conditions and processes far grander than those we currently model. Perhaps they formed in regions of incredibly high dark matter density, acting as immense gravitational wells that effortlessly drew in vast quantities of gas and stars. Or perhaps they are the result of countless galactic mergers over cosmic eons, a continuous process of accretion that built them into such magnificent proportions. Their very existence would push the boundaries of our cosmological models, forcing us to consider new mechanisms for cosmic growth and the intricate interplay of forces that shapes the universe's grandest structures. It's a thought that humbles us, reminding us that even the grandest structures we observe might be but fragments of something far, far larger, silently orchestrating the cosmic dance from beyond our current view. Another profoundly speculative idea that quietly resonates in the minds of cosmologists is that of dark galaxies. Imagine galaxies not as shimmering islands of light, but as vast, invisible entities composed almost entirely of dark matter, with very few, if any, ordinary stars. These ghostly galaxies would be nearly invisible to our current detection methods, which rely heavily on the light emitted by stars, gas and dust. It's like trying to find a shadow in a dark room. You know it's there because of what it affects, but you can't truly see it. We might infer their presence only through their subtle yet significant gravitational pull on surrounding visible matter, or perhaps by their influence on the cosmic microwave background radiation. The existence of such dark galaxies could provide critical new insights into the fundamental nature of dark matter itself, revealing its distribution, its interaction properties, and its profound role in the structure and dynamics of the cosmos. Could these dark galaxies harbor unique forms of dark chemistry, where hypothetical dark particles interact in ways completely unfamiliar to us? Could they even be home to dark life, entirely new forms of existence operating under physical principles radically different from those in our own luminous universe? These are deep, thought-provoking questions that push the boundaries of imagination. The existence of such structures would fundamentally alter our understanding of cosmic evolution and the distribution of matter and energy in the universe. It would suggest that the visible cosmos is merely a luminous frosting on a far vaster, darker, and more mysterious cake, silently shaped by unseen forces and teeming with hidden, unimaginable possibilities. Beyond the familiar classifications, there's a quiet whisper of galaxies with unconventional forms, structures that defy our neat categories and suggest a universe of boundless creativity. Imagine galaxies whose shapes are the direct result of unique or extreme conditions, forging them into cosmic anomalies. Perhaps there are galaxies with highly irregular shapes, far more chaotic and unpredictable than our current classification schemes of spirals, ellipticals, or lenticulars allow. These could be cosmic accidents born from incredibly violent and rapid mergers, or perhaps they formed in environments where gravity was unusually distributed, preventing them from settling into more familiar forms. Or perhaps these are galaxies that have undergone truly unusual evolutionary paths due to their extreme environment, such as intense gravitational interactions with neighboring galaxies, colossal cosmic collisions that leave behind tangled beautiful wrecks, or continuous interactions that pull them into bizarre, elongated streams. It is also possible that they exist in regions exposed to extreme radiation from a superactive quasar or a cascade of gamma-ray bursts influencing star formation and galactic structure in ways we've yet to comprehend. Such intense radiation could strip away gas-inhibit star formation or trigger bursts of star formation that radically reshape the galactic landscape. Think of a cosmic artist, not bound by conventional forms, sculpting nebulae into breathtaking, never-before-seen patterns. These are not merely variations on a theme. They represent a fundamental departure from the expected, challenging our understanding of galactic formation and evolution. Their discovery would force us to expand our models to reconsider the intricate interplay of forces that shapes these cosmic islands. Such galaxies would be profound testaments to the universe's boundless capacity for unexpected beauty and complexity, reminding us that even in the seemingly familiar realm of galactic forms, there remain countless wondrous surprises waiting to be gently unveiled. Then there are the primordial galaxies, whispers from the universe's earliest dawn, significantly different in composition and structure from those that formed much later. Imagine the cosmos in its tender infancy, a time before the universe was enriched with the heavy elements forged in the hearts of stars. These primordial galaxies, likely much smaller, less organized and more diffuse than their modern counterparts, would contain stars made almost entirely from hydrogen and helium, the universe's first, most fundamental elements. These are the first generations of stars blazing with an intensity and composition unlike anything we see today. They were the trailblazers, the pioneers that began the cosmic cycle of star formation and element creation, transforming the primordial soup into the first specks of light. Their detection would provide invaluable information about the universe's initial conditions, offering a direct glimpse into the very first moments of cosmic structure formation. How did these nascent galaxies coalesce from the primordial gas in a universe that was still incredibly hot and dense? What were the precise conditions that prevailed shortly after the Big Bang that allowed for their birth, and how did they overcome the pervasive uniform expansion to clump together? Studying them would be like examining the very first brushstrokes on the cosmic canvas, revealing the artist's initial intentions and the first steps in the universe's grand evolution. The light from these earliest galaxies would be incredibly redshifted, stretched by billions of years of cosmic expansion, making them extraordinarily faint and challenging to observe. Yet new generations of telescopes designed to capture these ancient whispers are on the horizon. Their discovery would not only confirm our models of early universe evolution, but also open a profound new chapter in our understanding of how the universe transformed from a homogeneous soup of particles into the complex galaxy-filled cosmos we inhabit today. These ancient faint lights are silent storytellers waiting to share the tale of cosmic genesis, a narrative that stretches far beyond our current sight. Finally, the captivating possibility of mirror galaxies, a truly mind-bending concept stemming from the speculative theory of a parallel universe or a mirror world, gently opens up fascinating avenues for exploration. Imagine for a moment that for every known particle and force in our universe, there exists a corresponding mirror particle and mirror force in a parallel reality, a realm subtly separated from our own. This concept suggests a profound duality to existence, where our universe is but one side of a cosmic coin. While entirely hypothetical and deeply embedded in theoretical speculation, these mirror galaxies would be composed of mirror matter, a kind of matter that interacts with our known universe in fundamentally different, almost imperceptible ways. Perhaps mirror matter interacts with our ordinary matter only through gravity, or through some incredibly weak, as yet undiscovered, mirror force, too faint to detect directly. This means we wouldn't see them with our telescopes, as their mirror light would not interact with our eyes or detectors. However, their presence might be subtly observable through indirect gravitational effects, perhaps by the gravitational lensing of light around an unseen mass that is not dark matter, or by unusual patterns in the movement of visible galaxies that can't be explained by our ordinary matter or even our known dark matter. They might also leave faint, telltale signatures in the cosmic microwave background if our universe subtly bumped into a mirror universe in its infancy, leaving a unique imprint. This profound concept challenges the very notion of what constitutes reality, suggesting that our universe might be just one half of a cosmic whole. The possibility of mirror galaxies invites us to consider a cosmos far more intricate and dualistic than we currently perceive, offering a tantalizing, almost poetic glimpse into realms where physics operates under subtly different mirrored rules, patiently awaiting our gentle, imaginative exploration. The universe, in its boundless creativity, might be capable of forms of existence we are only just beginning to imagine. In the pursuit of observing beyond the cosmic horizon, where the known begins to fade into the unknown, scientists and engineers are tirelessly pushing the very boundaries of technology. They are developing new instruments and methodologies delicately designed to pierce deeper into the universe than ever before, capturing the faintest whispers of ancient light. These remarkable technologies aim not only to enhance our view of the distant cosmos within our observable bubble, but also to potentially reveal regions that lie beyond the observable universe as we currently understand it. It's a grand patient endeavor, akin to building ever more sensitive ears to hear a song whispered from across an infinite void. One of the forefront technologies truly at the cutting edge of cosmic exploration is the next generation of extremely large telescopes, both those firmly anchored to our planet's surface and those gracefully orbiting in the silent vacuum of space. Ground-based observatories like the awe-inspiring Extremely Large Telescope ELT, currently being constructed in the high dry deserts of Chile, and the 30-meter telescope TMT, meticulously planned for Hawaii, aim to boast primary mirror diameters of around 30 to 40 meters. This is significantly larger than any current optical telescopes. These colossal mirrors will be capable of collecting far more light from incredibly faint, distant objects, allowing astronomers to patiently study the earliest galaxies and stars in unprecedented detail. Imagine collecting every single photon of light that has traveled for billions of years to reach us, painting a clearer picture of the universe's dawn. Simultaneously, the James Webb Space Telescope, JWST, magnificently launched in December 2021, represents the pinnacle of space-based observatories. With its enormous segmented mirror and instruments exquisitely designed to observe the universe primarily in infrared light, JWST has already begun to revolutionize our understanding. Infrared light has the remarkable ability to penetrate through the thick veils of cosmic dust clouds, which often obscure visible light, and to reveal galaxies formed shortly after the Big Bang. These are galaxies whose light has been stretched by the universe's expansion into longer, redder infrared wavelengths. These advanced telescopes are like cosmic time machines, allowing us to peer back into the universe's infancy, gathering invaluable data that might subtly hint at the structures and conditions of the cosmos even further beyond our current reach. Advancements in radio astronomy are also proving pivotal in gracefully extending our observational reach, allowing us to listen to the universe's low-frequency whispers. Imagine trying to hear the faintest echoes from the dawn of time. Radio waves, with their long wavelengths, can travel through vast amounts of gas and dust that block visible light, offering a unique window into these hidden realms. Projects like the Square Kilometer Array SKA, an immense international effort currently underway to build the world's largest radio telescope, are set to transform our understanding. The SKA will utilize thousands of individual dish antennas and up to 1 million low-frequency antennas meticulously spread over vast distances across South Africa and Australia. This distributed array will act as a single colossal radio ear, allowing the SKA to detect incredibly faint radio waves emanating from the cosmic dawn, the crucial era when the very first stars and galaxies finally began to form, illuminating the dark, nascent universe. These observations promise to shed invaluable light on the structure of the early universe, revealing how the first pockets of matter began to coalesce and radiate. The SKA's unparalleled sensitivity will also allow us to search for the faint hydrogen signal from billions of years ago, a direct probe of the universe's matter content before the first stars ignited. By listening to these ancient radio whispers, we hope to reconstruct the cosmic landscape as it was in its infancy, providing crucial context for understanding the immense unseen regions that lie beyond our current observational horizon. This patient listening, this gentle deciphering of cosmic echoes, is a profound testament to our persistent quest to understand the universe's full story from its very beginning to its grand, unseen expanse. Another incredibly promising technology opening entirely new windows onto the cosmos involves gravitational wave observatories. Facilities like LIGO Laser Interferometer, Gravitational Wave Observatory in the United States, and Virgo in Italy have already profoundly revolutionized astronomy by directly detecting gravitational waves, those elusive ripples in spacetime emanating from the colossal collisions of black holes and neutron stars. Imagine listening to the universe's most violent events, not with light, but with the very vibrations of space and time itself. These groundbreaking detections have confirmed a century-old prediction of Einstein's general relativity and ushered in a completely new era of multi-messenger astronomy, allowing us to observe the universe with both light and gravity. Future projects, like the ambitious Laser Interferometer Space Antenna LISA, a space-based gravitational wave observatory planned by the European Space Agency ESA, aim to detect gravitational waves from a wider range of cosmic sources. LISA will be sensitive to much lower frequencies of gravitational waves, allowing it to hear events like the mergers of supermassive black holes at the centers of galaxies or the subtle vibrations of white dwarf binaries within our own Milky Way. More profoundly, LISA is designed to potentially detect primordial gravitational waves, those incredibly faint ancient ripples generated in the universe's very first moments, even before the CMB was formed. These observations could offer direct, undeniable evidence of cosmic inflation, that rapid expansion shortly after the Big Bang, allowing us to probe the physics of the very early universe at energy scales far beyond what any particle accelerator can achieve. By listening to these primordial echoes, we might gain unprecedented insights into phenomena occurring beyond our current observational limits, truly hearing the deepest, most ancient songs of creation itself. Additionally, the gentle development of neutrino observatories marks another crucial frontier in our quest to understand the unseen cosmos. Imagine the universe not just as a place of light and gravity, but also as a teeming sea of incredibly tiny, almost massless particles called neutrinos. Observatories like the Ice Cube Neutrino Observatory at the South Pole, a massive detector embedded in a cubic kilometer of Antarctic ice, and proposed future projects aim to detect high-energy neutrinos from the most extreme cosmic phenomena. The remarkable property of neutrinos is their incredibly weak interaction with matter. They can escape from dense regions of space, like the fiery cores of exploding stars or the hearts of active galaxies, where light would be completely blocked. They are like cosmic messengers, carrying information directly from the universe's most violent and obscured events. Because neutrinos rarely interact with anything, they can traverse the universe from the most distant regions, without being absorbed, scattered, or significantly altered. This means they carry pristine information about their sources, even if those sources are incredibly far away beyond the reach of electromagnetic radiation. Detecting ultra-high energy neutrinos from such distant cosmic phenomena could offer unprecedented clues about the conditions of the early cosmos, perhaps even hinting at the existence of unseen structures or entirely new physics. These elusive particles are like silent time capsules, preserving secrets from regions of the universe that remain hidden from our light-based telescopes. Advances in neutrino astronomy promise to unveil the universe's deepest, most energetic secrets, providing us with a unique and powerful way to probe the vast unseen expanses that lie beyond our current observational horizon. Finally, the immense power of computational astrophysics and the meticulous development of sophisticated algorithms and simulations play an incredibly crucial role in gently extending our understanding of the cosmos, especially in realms we cannot directly observe. Imagine trying to understand a complex living ecosystem by only observing a tiny corner of it. To grasp the whole, you need to model its underlying rules and dynamics by seamlessly combining vast amounts of observational data from all those telescopes and observatories we discussed with incredibly detailed theoretical models of physics. Scientists can simulate the entire evolution of the universe from the chaotic moments of the Big Bang all the way to the present day. These incredibly complex simulations allow us to explore scenarios and structures that lie beyond our direct observational capabilities. For example, we can simulate the formation of the cosmic web, that intricate network of galaxies, gas, and dark matter under various conditions, testing different theories for the nature of dark matter or dark energy. We can explore what the universe might have looked like beyond our horizon based on the physics we understand within our bubble. These digital universes allow us to test hypotheses that are impossible to test through direct observation, pushing the boundaries of what we can infer about the unseen cosmos. Computational astrophysics therefore acts as a powerful bridge between the visible and the invisible, allowing us to paint a coherent picture of the universe's grand narrative, even in its most hidden chapters, and offering new insights into the nature of the universe beyond what is currently observable. The promise of quantum computing for exploring the cosmos is like a soft yet incredibly potent whisper of the future, suggesting entirely new ways to unravel the universe's deepest mysteries. Imagine a type of computer that doesn't just process information in simple bits of zeros and ones, but harnesses the peculiar and profound principles of quantum mechanics itself. Things like superposition being in multiple states at once, and entanglement being interconnected in a way that defies classical logic. Such power could fundamentally revolutionize our ability to understand the universe, especially its most complex and elusive phenomena. One of the primary ways quantum computing could profoundly aid in our exploration is through the simulation of cosmic phenomena. The universe, at its very deepest and most fundamental level, is governed by the intricate laws of quantum mechanics. From the gentle, intricate interactions within the blazing cores of stars to the chaotic yet precise behavior of particles in the incredibly hot, dense early universe, quantum processes are at play. Current classical computers, even the most powerful supercomputers, struggle to accurately simulate these incredibly complex quantum interactions across vast scales. However, quantum computers operating on these same peculiar quantum principles could simulate these cosmic processes with unprecedented accuracy and efficiency. This means we could potentially model the exact conditions of the Big Bang with a level of detail previously unimaginable, gaining profound insights into the universe's earliest moments. We could simulate the intricate formation of the first stars and galaxies, understanding how those primordial seeds truly blossomed into the structures we see today. Even more importantly, quantum computers could help us predict the behavior of dark matter and dark energy, those two enigmatic components that remain stubbornly beyond our current understanding. By running complex quantum simulations of their interactions, we might finally unlock their true nature, moving beyond inference to a deeper, more direct comprehension. These machines could be like cosmic crystal balls, allowing us to peer into the quantum heart of the universe, revealing secrets that classical methods can only hint at. Quantum computing could also dramatically enhance our ability to process astronomical data. Imagine the sheer volume of information being collected by the next generation of telescopes and observatories, both ground-based giants and sensitive space-based instruments. These facilities will generate vast quantities of data, literally petabytes and exabytes of raw information, far beyond the capacity of today's classical computers to analyze efficiently. It's like trying to drink from a fire hose with a teacup. Quantum computers, with their inherent ability to perform multiple calculations simultaneously through quantum parallelism, could gracefully sift through this immense cosmic data more effectively than anything we currently possess. They could identify incredibly subtle patterns and faint signals that might be completely missed by our current analytical methods. This could include the delicate detection of faint signals from the cosmic microwave background radiation, revealing even tinier fluctuations or anomalies that whisper secrets about the universe's infancy. Or perhaps they could uncover elusive gravitational waves that carry information about the universe's earliest moments. Waves so faint, they are almost undetectable by current means. By unlocking these hidden patterns, quantum computers could potentially reveal aspects of the cosmos that lie beyond the observable universe, providing us with data from realms that were previously considered entirely inaccessible. It's like having an incredibly sensitive cosmic ear that can pick up the softest, most ancient echoes, bringing to light the hidden symphony of the universe. Furthermore, quantum computing also holds immense promise for improving our fundamental understanding of the large-scale structure of the universe, that intricate, sprawling cosmic web. Imagine the universe not as a uniform space, but as a complex network of luminous filaments, vast empty voids, and dense knots of galaxies, gas, and dark matter, spanning the entire observable universe. Simulating the intricate formation and evolution of this colossal structure requires solving numerous incredibly complex equations that describe the ceaseless interaction of gravity, dark matter, and baryonic matter. The ordinary matter we know over billions of years. This involves tracking the movement and interaction of billions of particles over cosmic timescales, a task that stretches even the most powerful classical supercomputers to their limits. Quantum computers, with their superior processing power and ability to handle immense interconnected data sets, could tackle these simulations with greater detail and over much larger scales. They could help us to understand precisely how the universe's largest structures came to be, how they evolved over eons, and crucially, how they might extend beyond the observable limits. We could simulate vast unseen superclusters or predict the exact arrangement of dark matter filaments in regions we cannot directly observe. This deeper understanding of the cosmic web's formation and its unseen extensions would allow us to test various cosmological models, refine our theories of dark matter and dark energy, and ultimately paint a more complete and accurate picture of the universe's grand unseen architecture. Finally, the burgeoning field of quantum cryptography could provide an almost impenetrable layer of security for the immense amounts of data we collect in our cosmic explorations. Imagine the sensitive data transmitted between Earth and far-flung spacecraft, or between incredibly sophisticated telescopes distributed across the globe or even in space. This data, containing invaluable insights into the cosmos, needs to be protected from any interference or corruption. Quantum cryptography, by leveraging the fundamental principles of quantum mechanics, like the fact that observing a quantum system inevitably changes, it offers a truly unbreakable method for secure communication. It ensures the integrity of the vast amounts of data collected in our exploration of the cosmos, protecting it from any potential eavesdropping or malicious interference. This is crucial for maintaining the trustworthiness of our scientific discoveries as we push further into the unknown. It's like building an invisible, unbreakable shield around our cosmic communications, ensuring that the precious whispers from the universe reach us untainted, allowing us to truly build an accurate, uncorrupted picture of the cosmos from the smallest quantum fluctuations to the grandest unseen structures.